Hello and welcome to this course on Kubernetes for the absolute beginners. My name is Mumshad Manambeth and I will be your instructor for this course. So about me, I am a solutions architect and I work on cloud automation and DevOps practice. I am also a part-time trainer. I have authored multiple bestseller and top-rated courses on Udemy on topics like Docker and Ansible. Let's take a look at the structure of this course. This course contains a series of lectures on Kubernetes. We will be discussing the basic concepts of Kubernetes here. These are followed by some demos on setting up a test environment and getting started with Kubernetes. We have optional quizzes that test your knowledge after each lecture. These are completely optional. You don't have to pass these to continue with the course. We then have coding exercises that will help you learn and practice developing YAML files, which will enable you to develop Kubernetes configuration files yourself. These configuration files may be a bit tricky for beginners, so I will also provide some tips and tricks that will help you remember the format. This plus the coding exercises will give you enough confidence to develop your own configuration files. We will in fact spend some extra time on these configuration files because in order to work with Kubernetes, you must have a good understanding around it. At the end, you will be given an assignment to test your knowledge on the topic. The assignment will help you gain exposure in working on a real-life task with Kubernetes. And as always, if you have any questions, you may reach out directly to me through the Q&A section. So who is this course for? This is for the absolute beginner. You are not required to have any prior experience working with Kubernetes. We will walk through all the basic concepts required for you to understand Kubernetes. This is for those who are new to containers and container orchestration technology. You could be a developer trying to understand microservices, containers, and orchestration technology, looking to gain some hands-on experience in developing Kubernetes-based solutions. You could be a system admin looking to scale up your knowledge in container clusters and trying to get some hands-on experience in setting up such clusters. Or you could be a project manager looking to gain only a basic understanding of the underlying concepts. This is for any beginner starting his Kubernetes journey. So that brings us to the question on how you should take up this course. Depending on your interest and the time and resources you have at hand, you may choose to skip certain sections of the course. If you're already familiar with the basic concepts such as Docker containers and YAML files, feel free to skip those sections. In this course, we will see different ways of setting up Kubernetes on your local machine or on various cloud platforms such as Google Cloud or AWS. If you are in a hurry or do not have sufficient resources to set up your own instances, we will also see option available to spin up a Kubernetes cluster in a matter of seconds on the cloud. Moving on to the topics we will be covering. In this course, we will go through the basics of Kubernetes. We will try to understand what containers are and what container orchestration is. We will see different ways of setting up and getting started with Kubernetes. We will go through the various concepts such as pods, replica sets, deployments, and services. We will try and get a basic understanding of networking in Kubernetes. We will also spend some time working with kubectl command line utility and developing Kubernetes YAML definition files. And finally, we will see how to deploy a microservices application on a public cloud platform like Google Cloud. As always, feel free to go through this course at your own pace. There may be sections in the course that you may be familiar with already, so feel free to skip them. So let's get started and I will see you in the first module. Hello and welcome to this lecture on Kubernetes Overview. My name is Mumshad Manambeth and we are learning Kubernetes for beginners. In this lecture, we will go through an overview of Kubernetes. Kubernetes, also known as K8s, was built by Google based on their experience running containers in production. It is now an open source project and is arguably one of the best and most popular container orchestration technologies out there. In this lecture, we will try to understand Kubernetes at a high level. To understand Kubernetes, we must first understand two things: container and orchestration. Once we get familiarized with both of these terms, we would be in a position to understand what Kubernetes is capable of. We will start by looking at each of these next. We're now going to look at what containers are. Specifically, we will look at the most popular container technology out there, that is Docker. If you are familiar with Docker already, feel free to skip this lecture and move over to the next. Hello and welcome to this lecture on Docker Overview. My name is Mumshad Manambeth and we are learning Docker fundamentals. In this lecture, we're going to look at a high-level overview on why you need Docker and what it can do for you. Let me start by sharing how I got introduced to Docker. In one of my previous projects, I had this requirement to set up an end-to-end stack including various different technologies like a web server using Node.js, a database such as MongoDB, a messaging system like Redis, and an orchestration tool like Ansible. We had a lot of issues developing this application with all these different components. First, their compatibility with the underlying operating system. We had to ensure that all these different services were compatible with the version of the operating system we were planning to use. There have been times when certain versions of these services were not compatible with the OS, and we've had to go back and look for another OS that was compatible with all these different services. Secondly, we had to check the compatibility between these services and the libraries and dependencies on the OS. We've had issues where one service requires one version of a dependent library, whereas another service required another version. The architecture of our application changed over time. We've had to upgrade to newer versions of these components or change the database, etc. And every time something changed, we had to go through the same process of checking compatibility between these various components and the underlying infrastructure. This compatibility matrix issue is usually referred to as the matrix from hell. Next, every time we had a new developer on board, we found it really difficult to set up a new environment. The new developers had to follow a large set of instructions and run hundreds of commands to finally set up their environments. They had to make sure they were using the right operating system, the right versions of each of these components, and each developer had to set all that up by himself each time. We also had different development, test, and production environments. One developer may be comfortable using one OS and the others may be using another one. And so we couldn't guarantee that the application that we were building would run the same way in different environments. And so all of this made our life in developing, building, and shipping the application really difficult. So I needed something that could help us with the compatibility issue. Something that would allow us to modify or change these components without affecting the other components and even modify the underlying operating system as required. And that search landed me on Docker. With Docker, I was able to run each component in a separate container with its own libraries and its own dependencies, all on the same VM and the OS, but within separate environments or containers. We just had to build the Docker configuration once, and all our developers could now get started with a simple Docker run command. Irrespective of what the underlying operating system they run, all they needed to do was to make sure they had Docker installed on their systems. So what are containers? Containers are completely isolated environments, as in they can have their own processes or services, their own networking interfaces, their own mounts, just like virtual machines, except they all share the same operating system kernel. We will look at what that means in a bit. But it's also important to note that containers are not new with Docker. Containers have existed for about 10 years now, and some of the different types of containers are LXC, LXD, LXCFS, etc. Docker utilizes LXC containers. Setting up these container environments is hard as they are very low level, and that is where Docker offers a high-level tool with several powerful functions, making it really easy for end users like us. To understand how Docker works, let us revisit some basic concepts of operating systems first. If you look at operating systems like Ubuntu, Fedora, SUSE, or CentOS, they all consist of two things: an OS kernel and a set of software. The operating system kernel is responsible for interacting with the underlying hardware. While the OS kernel remains the same, which is Linux in this case, it's the software above it that makes these operating systems different. This software may consist of a different user interface, drivers, compilers, file managers, developer tools, etc. So you have a common Linux kernel shared across all operating systems and some custom software that differentiates operating systems from each other. We said earlier that Docker containers share the underlying kernel. What does that actually mean, sharing the kernel? Let's say we have a system with an Ubuntu OS with Docker installed on it. Docker can run any flavor of OS on top of it as long as they are all based on the same kernel, in this case Linux. If the underlying operating system is Ubuntu, Docker can run a container based on another distribution like Debian, Fedora, SUSE, or CentOS. Each Docker container only has the additional software that we just talked about in the previous slide that makes these operating systems different, and Docker utilizes the underlying kernel of Docker host, which works with all the operating systems above. So what is an OS that do not share the same kernel as this? Windows. And so you won't be able to run a Windows-based container on a Docker host with Linux OS on it. For that, you would require Docker on a Windows server. You might ask, isn't that a disadvantage then? Not being able to run another kernel on the OS? The answer is no, because unlike hypervisors, Docker is not meant to virtualize and run different operating systems and kernels on the same hardware. The main purpose of Docker is to containerize applications and to ship them and run them. So that brings us to the differences between virtual machines and containers, something that we tend to do, especially those from a virtualization background. As you can see on the right, in case of Docker, we have the underlying hardware infrastructure, then the operating system, and Docker installed on the OS. Docker can then manage the containers that run with libraries and dependencies alone. In case of a virtual machine, we have the OS on the underlying hardware, then the hypervisor like a ESX or virtualization of some kind, and then the virtual machines. As you can see, each virtual machine has its own operating system inside it, then the dependencies, and then the application. This overhead causes higher utilization of underlying resources as there are multiple virtual operating systems and kernels running. The virtual machines also consume higher disk space as each VM is heavy and is usually in gigabytes in size, whereas Docker containers are lightweight and are usually in megabytes in size. This allows Docker containers to boot up faster, usually in a matter of seconds, whereas virtual machines, as we know, takes minutes to boot up as it needs to boot up the entire operating system. It is also important to note that Docker has less isolation as more resources are shared between containers like the kernel, whereas VMs have complete isolation from each other. Since VMs don't rely on the underlying operating system or kernel, you can have different types of operating systems such as Linux-based or Windows-based on the same hypervisor, whereas it is not possible on a single Docker host. So these are some differences between the two. So how is it done? There are a lot of containerized versions of applications readily available as of today. So most organizations have their products containerized and available in a public Docker registry called Docker Hub or Docker Store already. For example, you can find images of most common operating systems, databases, and other services and tools. Once you identify the images you need and you install Docker on your host, bringing up an application stack is as easy as running a docker run command with the name of the image. In this case, running a docker run Ansible command will run an instance of Ansible on the Docker host. Similarly, run an instance of MongoDB, Redis, and Node.js using the docker run command. When you run Node.js, just point to the location of the code repository on the host. If you need to run multiple instances of the web service, simply add as many instances as you need and configure a load balancer of some kind in the front. In case one of the instances was to fail, simply destroy that instance and launch a new instance. There are other solutions available for handling such cases that we will look at later during this course. We've been talking about images and containers. Let's understand the difference between the two. An image is a package or a template, just like a VM template that you might have worked with in the virtualization world. It is used to create one or more containers. Containers are running instances of images that are isolated and have their own environments and set of processes. As we have seen before, a lot of products have been Dockerized already. In case you cannot find what you're looking for, you could create an image yourself and push it to the Docker Hub repository, making it available for the public.
If you look at it, traditionally, developers developed applications. Then they hand it over to ops team to deploy and manage it in production environments. They do that by providing a set of instructions, such as information about how the host must be set up, what prerequisites are to be installed on the host, and how the dependencies are to be configured, etc. The ops team uses this guide to set up the application. Since the ops team did not develop the application on their own, they struggle with setting it up. When they hit an issue, they work with the developers to resolve it. With Docker, a major portion of work involved in setting up the infrastructure is now in the hands of the developers in the form of a Docker file. The guide that the developers built previously to set up the infrastructure can now easily be put together into a Docker file to create an image for the applications. This image can now run on any container platform and is guaranteed to run the same way everywhere. So the ops team now can simply use the image to deploy the application. Since the image was already working when the developer built it and operations are not modifying it, it continues to work the same way when deployed in production. To learn more about containers, check out my other courses, Docker for the Absolute Beginners and Docker Swarm, where you can learn and practice Docker commands and create Docker files. That's the end of this lecture on containers and Docker. See you in the next lecture. Hello and welcome to this demo. In this demo, we are going to discuss how to set up a lab environment, a local lab environment on our laptop. So in this demo, I'm going to use Oracle VirtualBox to set up a local lab with a virtual machine, an Ubuntu virtual machine installed. It doesn't really necessarily have to be Oracle VirtualBox. You could use any virtualization technology that you're comfortable with. If you have other ideas in setting up your lab environment, maybe in your private cloud environment or on a public cloud setup, that is fine. You don't have to do this, but this is for those who do not have access to such environments and really want to set up a lab using virtual machines on their local machines or laptops. In this demo, we're going to look at how to install VirtualBox on your laptop and how to deploy an Ubuntu software on it. Okay, so we are at the download page for VirtualBox. If you go to www.virtualbox.org, you will get to this page, and this is the website for downloading Oracle VirtualBox. As you can see, Oracle VirtualBox is supported on Windows, Linux, Macintosh, and Solaris hosts. If you go to the downloads section, you will be able to see the various options for downloading and installing Oracle VirtualBox. I'm going to choose the Windows option, and I'm going to click it. When I click, it gives me this option to download the executable, which is the installer. I'm going to save it in one of the local folders. It's about 100 MB. Once it's downloaded, I'm going to run the executable, and it runs through the setup wizard. In the setup wizard, I'm going to click next, and then click next to select the location. I'm going to set the default values for the options. And finally, read this warning about network interfaces. It's going to reset the network connection, which is fine. And then I'm going to click install. And it goes through the installation process and is finally finished installing. Once I click on finish, it brings up the Oracle VirtualBox Manager user interface, and this is the interface that we will be using to set up new virtual machines. If you click on new, you'll actually get to see the options available for deploying a new virtual machine. So to deploy a new virtual machine, we need an image. So we do not have an operating system with us right now, or we don't have a disk. So we can actually download a readily available operating system image from the internet. And if you go to the website osboxes.org, you can actually find various images available for various operating systems. And so this site gives you readily available images for Oracle VirtualBox or VMware based virtualization platforms. So if you go to VM images at the top and select VirtualBox images, it will take you to this page where it lists all the various flavors of operating systems available. As you can see, there are many. And for our purposes, I'm going to go with Ubuntu. So click on Ubuntu and click on VirtualBox VDI image. That will take you to the download page for Ubuntu. Under this page, scroll down to various versions of Ubuntu operating system, and I'm going to go with version 16.04. And as you can see, it has various options for VirtualBox and VMware, VirtualBox being the default, and that's what I have, so I'm going to go with that. And I'm going to go with the 64-bit version. So click on download, and it actually downloads a .7z file. So remember that this is a compressed file, .7z, and it takes about 1 GB of disk space. So be aware of that. And if you look at it, it's a .7z file, so it's a zip file, so you need to extract it to use it. So I'm going to use the 7-zip extractor. I'm going to extract the image. And now I have the image extracted into a folder by the name Ubuntu, and under that I have a folder 64-bit under which I have the actual image file, which is with the extension .vdi. Now I could go back to my Oracle VirtualBox Manager user interface and deploy a new machine. I'm going to click on New to create a new virtual machine, and it brings up this user interface. And this is where you have to specify the name for your new virtual machine. I'm going to specify Ubuntu, and as you can see, it automatically sets the type to Linux and the version to Ubuntu 64-bit. Now, if you look at the version, you see that it automatically selected the 64-bit, which is what I wanted. But there's also a 32-bit, and as you can see, for each operating system flavors, you see a 32-bit as well as a 64-bit option. Now, in some cases, you may not see the 64-bit option, and that is because you most probably don't have the virtualization support on your system enabled. So most of the laptops have the virtualization support disabled by default, and you have to actually explicitly enable it.
So in my previous courses, a lot of students have reached out to me saying that they don't see the 64-bit option, and that is really because you do not have the virtualization technology enabled on your laptop. So in order to do that, you actually need to go to the BIOS and enable it from there. So for most laptops, it's actually a BIOS setting. And if you do not know how to do that, you could simply search in Google, search enabling virtualization technology, and it'll come up with a lot of options. Put the model of your laptop and you might see the ones specific to your laptop. In most of the cases, it's in the BIOS, and it's an advanced feature in BIOS where you see the virtualization technology, and that's where you go in and enable it. So this is another. So these are some examples of how the virtualization technology option looks in the BIOS. And once you do that, when you come back and look at your this screen, you should be able to see the 64-bit option available. So I'm going to select the 64-bit Ubuntu version and go ahead. And if you look at the memory size, I'm going to set a 2 GB of memory, and then I'm going to go ahead and select the hard disk. So for this, you need to click the use an existing hard disk, because we're not actually going to start with a blank hard disk. We actually have the image downloaded, so that's going to be our hard disk. Whatever we downloaded and extracted, that's going to be our hard disk. So click on browse and browse the file that you just downloaded and extracted with the extension .vdi, and it has to be a 64-bit version, so make sure you select that and then click on OK. Now it has deployed the Ubuntu image, or the Ubuntu virtual machine, and before powering it up, as you can see, it's currently powered off, and before powering it up, I'd like to go into the settings page and set a few things, so specifically around network. So I'd like to enable, go to the network page and set the network type to bridged. By default it is NAT, and I want to change that and set it to bridged adapter. And the adapter that it's going to bridge to is the my Wi-Fi router, my Wi-Fi adapter. So I'm going to bridge the network interface on the Ubuntu virtual machine to the network, the wireless network adapter on my laptop. Before powering it up, I'm just going to take a snapshot. This is something I do. I just create, I just take a snapshot whenever I can, just so in case I had to come back, I could do that. So I just took a snapshot named before initial setup, and I'm just now going to start my virtual machine. So my virtual machine is now powered up. I'm going to log in using the user osboxes.org, and the password is also osboxes.org, all lowercase. That's actually the name of the site where we downloaded the image from. And once we are in, I'm going to open up a terminal, and the first thing that I would like to do is identify the IP address of the VM. So if I run the ifconfig command, I can see that the IP address is 192.168.1.84. That's the IP that was assigned to the virtual machine by my wireless router, because I bridged the network connection from the VM to my wireless router. I'm now going to try and SSH into it, so I'm going to use a terminal. The one that I'm using here is called MOBA Xterm. It's a free software. I actually kind of like it because I can do a lot of configurations on my SSH sessions with this. You don't really have to use it. You could use any SSH terminal, just like PuTTY, for example. You could simply use PuTTY to SSH into the virtual machines. I'm going to use the IP address 192.168.1.84. Before going into that, I'm just going to look at my IP address. So my laptop has an IP 192.168.1.70 on the same network. So my laptop and the virtual machine are on the same network, which is created by my Wi-Fi router. And so I should be able to really SSH into it. So I'm going to try to do that right now. I'm going to put in the IP of the host, and then the username is osboxes. I'm going to click on OK. And as you can see, it doesn't really connect. It says connection refused. So if I go back to my Ubuntu VM and see the SSH service, because this is most likely an issue with the SSH service. So I'm going to try and see if the SSH service is enabled, and if it's running, I'm going to run the service SSH status command, and as you can see, it doesn't really see, it says there is no such file or directory. So the SSH service is not set up. I'm going to do that right now, so I'm going to run the apt get update command to update my internal repositories, followed by the command to install SSH service on my Ubuntu VM. So I'm going to run the apt get install OpenSSH server. OpenSSH server is a package that installs SSH service on my Ubuntu VM. And as you can see, it's finished successfully. And if I now run the service SSH status command, I can see that it's active and in a running state. So that is good. I can now go back and try to restart my session. I'm going to press the R key to restart the session, and as you can see, I'm at a login prompt now. I'm going to type in the password, which is osboxes.org, and there you go. I'm logged in. I'm logged into my Ubuntu VM from my laptop using an SSH. That's it for this demo. I will see you in the next demo. Hello and welcome to this demo. In this demo, we're going to see how to install Docker on an Ubuntu virtual machine. So it's a very simple demo. We're going to see, we've already seen how to set up an Ubuntu virtual machine. Now once we have that, the next step is to install Docker. So in this demo, we're going to see how to install Docker. I'm logged into my Ubuntu VM from my laptop using an SSH. Okay, I'm now going to become the root user, so I'm going to run the sudo su command, and I'm going to become the root user. The next part is to install Docker on my host. In order to do that, I need to install the Docker package. For that, I need to run the command apt-get install, and the package name is docker.io. When I run this command, it goes out and fetches all the prerequisites required by Docker and installs all of that in on my Ubuntu virtual machine. I'm just going to wait for it to finish. Okay, so it's finished installing Docker. If I now run the command docker, it's actually going to show me the help page. If I run docker version, it's going to show me the version of Docker installed on my Ubuntu virtual machine. So it's actually that simple. Simply run the apt install docker.io command. Now I'm going to spin up a Docker container. I'm going to run the command docker run hello world, and it's going to pull up the hello world image and print me a message. It says hello from Docker, and that's all that the hello world container does. I could actually try something else. I could try some other container that's a bit more fun. So I'm going to run another Docker image called whalesay, and all that it does is it prints me a graphic image of a whale who's saying something, and it prints me a graphic image of a whale, which is the Docker whale, saying boo. Well, that's it for this demo. It's a pretty simple demo of installing Docker and running a Docker container. That's it for this demo. I will see you in the next demo. Hello and welcome to this lecture on container orchestration. My name is Mumshad Manambeth, and we are learning Kubernetes for beginners. In this lecture, we will talk about container orchestration. So we learned about containers, and we now have our application packaged into a Docker container. But what's next? How do you run it in production? What if your application relies on other containers such as databases or messaging services or other backend services? What if the number of users increase and you need to scale your application? How do you scale down when the load decreases? To enable these functionalities, you need an underlying platform with a set of resources and capabilities. The platform needs to orchestrate the connectivity between the containers and automatically scale up or down based on the load. This whole process of automatically deploying and managing containers is known as container orchestration. Kubernetes is thus a container orchestration technology. There are multiple such technologies available today. Docker has its own tool called Docker Swarm, Kubernetes from Google, and MesOS from Apache. While Docker Swarm is really easy to set up and get started, it lacks some of the advanced features required for complex applications. MesOS, on the other hand, is quite difficult to set up and get started, but supports many advanced features. Kubernetes, arguably the most popular of it all, is a bit difficult to set up and get started, but provides a lot of options to customize deployments and supports deployment of complex architectures. Kubernetes is now supported on all public cloud service providers like GCP, Azure, and AWS, and the Kubernetes project is one of the top-ranked projects in GitHub. There are various advantages of container orchestration. Your application is now highly available as hardware failures do not bring your application down because you have multiple instances of your application running on different nodes. The user traffic is load balanced across the various containers. When demand increases, deploy more instances of the application seamlessly and within a matter of seconds. And we have the ability to do that at a service level. When we run out of hardware resources, scale the number of underlying nodes up or down without having to take down the application. And do all of these easily with a set of declarative object configuration files. And that is Kubernetes. It is a container orchestration technology used to orchestrate the deployment and management of hundreds and thousands of containers in a clustered environment. Don't worry if you didn't get all of what I just said. In the upcoming lectures, we will take a deeper look at the architecture and various concepts surrounding Kubernetes. That is all for this lecture. Thank you for listening, and I will see you in the next lecture. Hello and welcome to this lecture. My name is Mumshad Manambeth and we are learning Kubernetes for beginners. Before we head into setting up a Kubernetes cluster, it is important to understand some of the basic concepts. This is to make sense of the terms that we will come across while setting up a Kubernetes cluster. Let us start with nodes. A node is a machine, physical or virtual, on which Kubernetes is installed. A node is a worker machine, and that is where containers will be launched by Kubernetes. It was also known as minions in the past, so you might hear these terms used interchangeably. But what if the node on which your application is running fails? Well, obviously our application goes down. So you need to have more than one node. A cluster is a set of nodes grouped together. This way, even if one node fails, you have your application still accessible from the other nodes. Moreover, having multiple nodes helps in sharing load as well. Now we have a cluster, but who is responsible for managing the cluster? Where is the information about the members of the cluster stored? How are the nodes monitored? When a node fails, how do you move the workload of the failed node to another worker node? That's where the master comes in. The master is another node with Kubernetes installed in it and is configured as a master. The master watches over the nodes in the cluster and is responsible for the actual orchestration of containers on the worker nodes. When you install Kubernetes on a system, you're actually installing the following components: an API server, an etcd service, a kubelet service, a container runtime, controllers, and schedulers. The API server acts as the front end for Kubernetes. The users, management devices, command line interfaces all talk to the API server to interact with the Kubernetes cluster. Next is the etcd key store. etcd is a distributed, reliable key value store used by Kubernetes to store all data used to manage the cluster. Think of it this way. When you have multiple nodes and multiple masters in your cluster, etcd stores all that information on all the nodes in the cluster in a distributed manner. etcd is responsible for implementing logs within the cluster to ensure that there are no conflicts between the masters. The scheduler is responsible for distributing work or containers across multiple nodes. It looks for newly created containers and assigns them to nodes. The controllers are the brain behind orchestration. They are responsible for noticing and responding when nodes, containers, or endpoints goes down. The controllers make decisions to bring up new containers in such cases. The container runtime is the underlying software that is used to run containers. In our case, it happens to be Docker, but there are other options as well. And finally, kubelet is the agent that runs on each node in the cluster. The agent is responsible for making sure that the containers are running on the nodes as expected. So far, we saw two types of servers, master and worker, and a set of components that make up Kubernetes. But how are these components distributed across different types of servers? In other words, how does one server become a master and the other the slave? The worker node, or minion as it is also known, is where the containers are hosted. For example, Docker containers. And to run Docker containers on a system, we need container runtime installed. And that's where the container runtime falls. In this case, it happens to be Docker. This doesn't have to be Docker. There are other container runtime alternatives available, such as Rocket or Cryo. But throughout this course, we are going to use Docker as our container runtime engine. The master server has the kube API server, and that is what makes it a master. Similarly, the worker nodes have the kubelet agent that is responsible for interacting with the master to provide health information of the worker node and carry out actions requested by the master on the worker nodes. All the information gathered are stored in a key value store on the master. The key value store is based on the popular etcd framework as we just discussed. The master also has the control manager and the scheduler. There are other components as well, but we will stop there for now. The reason we went through this is to understand what components constitute the master and worker nodes. This will help us install and configure the right components on different systems when we set up our infrastructure. And finally, we also need to learn a little bit about one of the command line utilities known as the kube command line tool, or kubectl, or kube control as it is also called. The kube control tool is used to deploy and manage applications on a Kubernetes cluster, to get cluster information, to get the status of other nodes in the cluster, and to manage many other things. The kubectl run command is used to deploy an application on the cluster. The kubectl cluster info command is used to view information about the cluster, and the kubectl get nodes command is used to list all the nodes part of the cluster. That's all we need to know for now, and we will keep learning more commands throughout this course. We will explore more commands with kubectl when we learn the associated concepts. For now, just remember the run, cluster info, and get nodes commands, and that will help us get through the first few labs. That's it for this lecture. I will see you in the next lecture. Hello and welcome to this lecture on setting up Kubernetes. My name is Mumshad Manambeth and we are learning Kubernetes for beginners. In this lecture, we will look at the various options available in building a Kubernetes cluster from scratch. There are lots of ways to set up Kubernetes. We can set it up ourselves locally on our laptops or virtual machines using solutions like Minikube and kubeadmin. Minikube is a tool used to set up a single instance of Kubernetes in an all-in-one setup, and kubeadmin is a tool used to configure Kubernetes in a multi-node setup on our local machines. We will look more into that in a bit. There are also hosted solutions available for setting up Kubernetes in a cloud environment such as GCP or AWS. We will also have some demos around those. And finally, if you don't have the resources or if you don't want to go through the hassle of setting it all up yourself and you simply want to get your hands on a Kubernetes cluster instantly, check out playwithk8s.com. I also have a demo on this. So feel free to choose the one that is right for you. You need not go through all the demos. Pick the ones that best suit your needs based on your time and resources. We will start with Minikube, which is the easiest way to get started with Kubernetes on a local system. If Minikube is not of interest to you, now would be a good time to skip this lecture. Before we head into the demo, it's good to understand how it works. Earlier we talked about the different components of Kubernetes that make up a master and worker nodes, such as the API server, etcd key value store, controllers and schedulers on the master, kubelets, container runtime on the worker nodes, etc. It would take a lot of time and effort to set up and install all of these various components on different systems individually by ourselves. Minikube bundles all of these different components into a single image, providing us a pre-configured single-node Kubernetes cluster so we can get started in a matter of minutes. The whole bundle is packaged into an ISO image and is available online for download. Now, you don't have to download it yourself. Minikube provides an executable command line utility that will automatically download the ISO and deploy it in a virtualization platform such as Oracle VirtualBox or VMware Fusion. So you must have a hypervisor installed on your system. For Windows, you could use VirtualBox or Hyper-V, and for Linux, you could use KVM. And finally, to interact with the Kubernetes cluster, you must have a kubectl Kubernetes command line tool also installed on your machine. So you need three things to get this working. You must have a hypervisor installed, a kubectl command line utility installed, and Minikube executable installed on your system. So let's get into the demo. Hello and welcome to this demo. In this demo, we're going to see how to deploy a basic version of Kubernetes using the Minikube utility. We first go to the Kubernetes website, which is kubernetes.io. And if you look at the website, you see a lot of very basic information about Kubernetes. What we need is instructions on installing Minikube. So we go into the documentation section, and here at the top on the left you see the setup section, and this is where we have documentation about the various options available to install Kubernetes and get started with Kubernetes. So if you look here, you have instructions for setting up on a local machine and various hosted solutions, various turnkey solutions available for Kubernetes. And what we are interested in is Minikube, which is an option for setting up Kubernetes on a local machine. This is what we are going to get started. So here you have information about running Kubernetes locally on using Minikube. And the first thing that we need to do is install Minikube, so we're going to go into that. If you look here, you see that before you begin, you must have virtualization technology enabled in your computer's BIOS. We actually discussed this in one of the previous demos. So you must make sure that you have the virtualization technology installed or enabled on your laptop. So you most probably need to go into your BIOS setting and make sure that it's enabled. There's actually a way to confirm that if you go into your hypervisor, such as a VirtualBox. In my case, I have VirtualBox installed on my laptop, and which is also a prerequisite for configuring Minikube. You actually need a hypervisor. It could either be VirtualBox, VMware Fusion, or KVM. Since VirtualBox is supported on all the three flavors, such as OS X, Linux, and Windows, I actually went with VirtualBox. So if you go to VirtualBox and if you try to deploy a new virtual machine by clicking on the new button, you can actually see if under the versions, if you see a 64-bit, then you most likely have virtualization technology enabled. If you don't see a 64-bit, then you may not have it enabled. So that's actually one way to check if virtualization technology is enabled on your system. So those are two requirements. The next one is to install kube control, which is the kubectl command line utility. So if you click on install kubectl, you see instructions on installing kubectl. In our case, I have a Windows environment, so I'm going to click on Windows to get instructions on installing kube control command line tool. Well, basically, it's not really an installation. It's just an executable that you have to download. So if you click on the link, it actually downloads the executable. You just have to save it locally on your laptop. Now, when working with Minikube, I've had issues with saving the files on any other drive other than C drive. So I would recommend to save the kube control as well as the Minikube installation files or executable files in the C drive. So under C drive, I'm going to create a folder called Kubernetes, and I'm going to save the kube control executable file there. Okay, so that's good. The next step, as you can see, is to install Minikube. Again, installing Minikube is very easy as well. It's not really an installation. You just have to download the executable. I'm going to go into the versions available and find the one for Windows, and that is Minikube Windows-AMD64. I'm going to click on that. I'm going to save it next to the same kube control executable, and as soon as it's downloaded, I'm going to rename the file to minikube.exe. So it's actually an executable that you're downloading, but it's just not, it just doesn't have the exe extension. So I'm just going to download and rename it to minikube.exe. So that's done. I'm now going to go back to the documentation, and if I go back to the first page on getting started with Minikube, I can actually see the quick start guide. So I'm done with the installation of Minikube. The next step is to start working with it. As you can see, the instruction says run the Minikube start command. What I'm going to do is I'm going to arrange my windows side by side. So my Oracle VirtualBox Manager, I'm going to put it on the left, and the command prompt where I'm going to run the command, I'm going to put it on the right. Now before I go ahead and run the Minikube start command, I just want to tell you what's going to happen. So I have my Oracle VirtualBox Manager installed on my laptop, but I don't have to manually go in and create any kind of virtual machines. As we discussed in the lecture, Minikube is going to automatically pull down the required Minikube image from the internet and deploy it as a virtual machine on my Oracle VirtualBox Manager. So I don't have to do anything manually. All I need to do is make sure that I have Oracle VirtualBox installed and working on my laptop, and then I downloaded the two executables, and they're both on my C drive and in a folder named Kubernetes next to each other. And all I need to do is run the minikube.exe start command. And as you can see, it's going to this is where it downloads the Minikube ISO, and as you can see on the left, it's actually created the Minikube image or virtual machine and is running it right now. And it's now going to do all the post configuration tasks, such as getting the IP address and configuring the cluster and local kube, etc. So it's basically getting the Kubernetes cluster set up right now. And there you go, it's done. Now we have the Kubernetes cluster, which is a single node cluster installed and configured in a matter of minutes. I'm going to now go back to my documentation and find the next instruction. As you can see, we're already done with the first step, which is minikube start, and I'm now going to run the next command. For now, I'm just simply going to copy these commands and run them, and just to make sure everything is working. We're not going to see what these commands do exactly, because we have a lot of lectures and demos that are coming up specifically on these topics, on how to run a container with Kubernetes, how to work with the kubectl command line tool, how to create services and deployments, and all of that. For the sake of this demo, we're just going to follow these blindly. So we're just going to just to make sure our environment is working. So I'm just going to copy the command kubectl run, and I'm going to run that. And before I do that, I'm just going to run a few commands. So if I run the kubectl get nodes command, it actually lists all the nodes in my cluster. In this case, you see the minikube node. That's the only node that's on my cluster, which is what I intended to do, and it's in a ready state, which means we're good. And if I run the kubectl get pods command, I see that there are no pods running. We'll look at what pods are later in this course. For now, I'm just going to run the command that I was told to run, and it says deployment hello minikube created. And if I run a kubectl get pods command, I see that it's actually created a pod, which is basically a container. And right now I see that it's in a running state, which is good. It's actually a web server, so I'm going to need to access the web page, and in order to do that, I'm going to run this command called kubectl expose deployment. And so I copy the command and I run that, and it says the service is exposed. So how do I access the web page? In order to do that, I'm going to run the command minikube service hello minikube-url, and it gives me a URL that I can use to access the web page. So the IP address is actually the IP address assigned to the minikube VM, which is 192.168.99.101, and the port where my web server is exposed is 32688. And if I use that combination in a browser, I can actually reach the web page. So there you go, it's working. And before I finish, I'm actually going to clean up. So I'm going to run the delete deployment command to delete whatever I just deployed, and it says it's deleted. And I'm just going to clear my screen. Okay, so that's it for this demo. We deployed the Kubernetes cluster using minikube, and it's in a working condition. We can now use this cluster going forward for all our exercises and labs going forward. So this is just one way of setting up. This is a really easy way of setting up a single node cluster. If you're interested in deploying a multi-node cluster, then we have other demos and lectures coming up on those. So feel free to choose whatever you're comfortable with. Thanks for your time, and I will see you in the next lecture. Hello and welcome to this lecture on setting up Kubernetes with kubeadm tool. In this lecture, we will look at the kubeadmin tool, which can be used to bootstrap a Kubernetes cluster. With the minikube utility, you could only set up a single node Kubernetes cluster. The kubeadmin tool helps us set up a multi-node cluster with master and workers on separate machines. Installing all of these various components individually on different nodes and modifying the configuration files to make it work is a tedious task. Kubeadmin tool helps us in doing all of that very easily in an automated fashion.
Before we head into the demo, it's good to understand how the whole process works. Let's go through the steps. First, you must have multiple systems or virtual machines created for configuring a cluster. We will see how to set up your laptop to do just that if you're not familiar with it. Once the systems are created, designate one as master and others as worker nodes. The next step is to install a container runtime on the hosts so that we can run containers on these hosts. We will be using Docker, so we must install Docker on all the nodes. The next step is to install kubeadmin tool on all the nodes. The kubeadmin tool helps us bootstrap the Kubernetes solution by installing and configuring all the required components in the right nodes. The third step is to initialize the master server. During this process, all the required components are installed and configured on the master server. That way, we can start the cluster level configurations from the master server. Once the master server is initialized and before joining the worker nodes to the master, we must ensure that the network prerequisites are met. A normal network connectivity between the systems is not sufficient for this. Kubernetes requires a special network between the master and worker nodes, which is called as a pod network or a cluster network. We will learn more about this network in the networking section later in this course. For now, we will simply follow the instructions available to get this installed and set up in our environment. The last step is to join the worker nodes to the master node. We are then all set to launch our application in Kubernetes. We will now see a demo of setting up Kubernetes using the kubeadmin tool in our local environment. Now, this demo is divided into multiple parts. In the first section, we will look at how to set up a basic lab in our laptop using a virtualization technology, and in our case, we're going to use VirtualBox. In fact, all that we need is 3 Linux virtual machines running a supported version of the operating system. In our case, we're going to use Ubuntu. You don't have to follow or you don't have to go through the initial demo of setting up the virtual machines, because that's for the absolute beginners. In case you already know how to do that, you can set up your virtual machines either on your laptop, or you could set it up on a lab environment or on the cloud. So it doesn't really matter where you do it. All you need to do is make sure that these 3 VMs, they have their own unique IP addresses, static IP addresses, they have their unique host names, and they're part of the same network so that they can communicate with each other. So we will have 3 sections in the demo. The first section to set up a basic lab environment, that's for the absolute beginners. And once we do that, we will then look at how to use the kubeadmin tool to set up and configure Kubernetes on that. Okay, thank you for your time, and I will see you in the demo. Hello and welcome to this demo. In this demo, we're going to see how to set up a Kubernetes cluster using kubeadmin tool. Kubeadmin is used to easily bootstrap a Kubernetes cluster. So this demo is actually divided into 2 sections. This part, which is the first part, is where we set up the prerequisites. So kubeadmin requires a set of virtual machines to deploy Kubernetes on. So we're going to have to deploy multiple virtual machines where we'll have one master and multiple worker nodes. So we need to set up our lab environment, which is our local lab environment based on VirtualBox and on our laptops. And we need to set it up to satisfy all the prerequisites that are required for kubeadmin. Now, you don't have to follow this procedure of using VirtualBox. You could use any of virtualization technology as you prefer. You don't even have to have it on your laptop. You could have it in a lab environment or on a cloud environment. It doesn't really matter. All you need is 3 VMs, each with unique host names and unique IP addresses, static IP addresses. And we are using Ubuntu virtual machine, so you could have Ubuntu or any other supported virtual machines
for Kubernetes. So if you have your own ideas of setting up lab, go ahead. You can skip this lecture and go ahead right now and meet me in the next demo and work with me to set up Kubernetes using kubeadmin tool. Okay, so we'll go back to the Kubernetes documentation page at kubernetes.io and click on documentation. We'll go to setup, and under setup we'll actually go to the left hand side section where we have setup and expand the independent solutions. And as you can see, the first option there is via Minikube, which is what we already saw, and the second option is bootstrapping cluster with kubeadmin tool. And so we're going to click on that, and that is where we have all our instructions. So when you click on that, you see the installing kubeadmin section, and this is where we will begin. The first section, as you see, says before you begin, and these are some of the prerequisites, and this is what we're going to work on in this video. Firstly, one or more machines running on any of these operating system flavors. So what we have is the first one, which is Ubuntu 16.04. So we already have the images for that, so we can use that to create multiple virtual machines. Each virtual machine must have 2 GB or more of RAM, 2 CPUs, full network connectivity between the machines in the cluster. It must have unique host names, MAC addresses, and product UUIDs. And we're going to make sure we do, we meet all of these requirements. And we are also going to make sure we have a unique static IP address assigned for all of the virtual machines. And certain ports must be open and swap disabled. So that is the last prerequisite. Okay, so we're going to, as the first step, we're going to deploy multiple virtual machines for our use. So for the sake of understanding, I've put together this slide with the various steps involved in setting up Kubernetes using the kubeadmin tool. So as you can see, there are 6 steps. The first is to deploy and identify a few virtual machines. So we're going to have one master and we're going to have 2 worker nodes. So that's the first step. And then the next step is to install Docker on them. The third is to install the kubeadmin tools on them. And then we initialize the master, create a pod network, and join the worker nodes to the master. So this is the high-level steps that we'll be following to set up this lab environment. So here we are at the first step where we're deploying virtual machines. In my Oracle VirtualBox Manager, I'm going to click on New to create a new virtual machine. I'm going to name it as Kube-Master, and that's going to be my first virtual machine. As we saw in the prerequisite, the amount of memory should be 2 GB or more, so I'm going to set the memory to 2 GB and click on Next. And I'm going to use an existing virtual hard disk file. This is what we already have, what we used in our previous lab environment. So I'm going to use the Ubuntu 16.04 64-bit image, which is the .vdi file. So I now have my master VM created, and before I power it on, I'm going to go into the settings and make a few changes. So if you go into the system section, you can go into the processor, and as you can see, you need to have 2 CPUs. That was one of the prerequisites. So I'm going to move the CPU to 2 CPU. I already have memory assigned as required, and I'm going to go into the network section. I'm going to set up a bridged adapter. So the default option is NAT. I'm going to change that to set it to bridge, and it's actually going to bridge to my wireless adapter, which connects to my Wi-Fi router, and that way I can access the internet. So all of my virtual machines must have internet connectivity so that I can install the prerequisites, etc. So I'm done with the settings. I'm now going to take a snapshot. This is a good practice. So before powering it on initially, I'm just going to take an initial snapshot so that in case something goes wrong, I can come back to my original state. And then I'm just going to right click and start my virtual machine. My virtual machine is now powered up. I'm going to log in using the default user password, which is osboxes.org. Once it's powered up, I'm going to open a terminal window. I'm going to search terminal and open a terminal window. And I'm going to run the ifconfig command to see the IP address assigned to it. As you can see, it's got an IP address 192.168.1.86 assigned to it, which is good. And that's the IP address assigned through my bridged adapter. I'm now going to see if the SSH service is running, because by default, these Ubuntu systems do not have SSH service running. And as a result, you will not be able to SSH into that. So we need to be able to SSH into that VM. So I'm going to have to install SSH service. I've already explained this in one of the previous demos, so I'm going to skip that for now, and I'm just going to install SSH myself. And so now I have installed SSH, and I'm going to run the service SSH status command, and as you can see, the SSH service is active and is running. I should now be able to SSH into this VM. I'm going to use the IP address to SSH into it using my SSH terminal application. I'm going to use the username osboxes. And I'm now at a login prompt. I'm going to input the password, which is osboxes.org. Okay, once I confirm that I'm able to SSH into it, I'm now going to shut it down. So I'm going to run the shutdown now command to shut down my server. The reason is I'd like to use this as a template to clone other virtual machines. We only have one master deployed for now. I'd like to deploy 2 other worker nodes. So I'm going to right click and click on clone. I'm going to name the new machine that will be cloned out of the master as node 1. So I'm going to name it cube-node 1. And remember to check the reinitialize the MAC address of all network cards option. This is required because each virtual machine must have a unique MAC address, and that is a prerequisite. And so checking this will help us with that. And the clone type, there are 2 options available, full clone and linked clone. If you have not worked with this before, the difference between the 2 is that a full clone creates a full copy of your virtual hard disk, that way consuming a lot more space on your hard disk, whereas a linked clone it does not really create a full copy of the virtual hard disk file, so that way it only consumes a minimal amount of disk space. So I'll go with a linked clone. That's going to be sufficient for our use case. And so there it has created a clone. I'm going to create another clone for my second node, and I'm going to name it cube-node 2, and make sure to check the reinitialize MAC address option, and I'm going to select a linked clone option as well for this. So now I have all the 3 virtual machines. I'm going to power up all of them right now. Okay, so my master as well as the nodes are all powered on, and I'm logged into it. I'm now logged into my master, and when I run the ifconfig command, I can see that it has the same IP address as before. If I look at the other virtual machines, they also have an IP assigned to them. My node 1 is 192.168.1.92, and I'm going to try and SSH into it just to make sure I'm able to do that. Okay, so I confirmed that I'm able to SSH into all of my nodes, which is good. The next step is to set host names, unique host names for these. As you can see, all of them have the same host name, which is osboxes, which is the default host name. So I need to set the right host name for each of them. What I'm going to do is first I need to be the root user. You need to do 2 steps to set the host name for each node. So you need to go into the file /etc/hostname and update the host name in the file. Only then the host name is going to be persistent across reboots. So I'm going to use the VI editor and go into etc hostname, and I'm going to delete the existing name, and I'm going to name my master as cube master. I will now save that. The second step is to go into the etc hosts file and update the host name here. As you can see, you still have a OS boxes name there, so you're going to rename that to Kube Master. And then I'm going to shut down my system. Okay, and I'm going to do the same with the other nodes. I'm going to edit the etc hostname file and name my worker node, the first worker node, to Kube node 1. And then I'm going to rename the host name in the etc hosts file. I'm going to remove that and name it as Kube node 1. And I'm going to shut down that host. And I'm now going to go to the third node, which is node 2. And I'm going to repeat the steps to update the host name on this node. Okay, so I have updated the host name on all the nodes, and they're all powered off. Now, I actually powered them off instead of rebooting them because there's something that I want to do next. Now, so far, these hosts or these virtual machines have an IP address assigned to them, which are actually from the bridged adapter on my Wi-Fi router network. So the IP addresses that these virtual machines are getting, which is in the 192.168 range, is actually the IP assigned by my Wi-Fi router at my home. Now, these IP addresses are provided by the DHCP service on my Wi-Fi router, so they can change. They're dynamic and they're not guaranteed to be the same IP addresses every time. So sometimes when you reboot these hosts, when they come back up, they may have a different IP address than the one that they had before. So this is not going to work well with Kubernetes because the communication between the master and the workers are through the network, internal network, and they rely on these IP addresses to communicate with each other. So these hosts must have a static IP address assigned to them. Now, I cannot achieve this with my bridged network, so I do not have an option to assign a static IP address on that network or on my Wi-Fi router. I do not want to mess with my Wi-Fi router. So an alternate way is to create a new network, which is a host-only network that will be used as the Kubernetes network for the interaction or communication between these nodes. And so when I create a new host-only network, I can actually disable the DHCP on that network. It will be a network created inside my laptop, and my laptop will have an interface, a virtual interface on that network, and all of these virtual machines will have a virtual interface on that network, and I can assign static IP addresses for these VMs on that network. So in order to do that, you need to go into Global Tools, click on Global Tools in the top right corner of the Oracle VirtualBox Manager interface, and there you'll see a list of networks, host-only networks that are already created. Sometimes you may have one that is created by default. If that is the case, you can actually use that, or if it's not there, you can click on the Create button to create a new virtual host-only Ethernet network. In this case, I'm just going to go ahead and use the same one, which is in the range 192.168.56.1. And you can see the DHCP server option is unchecked. So make sure that you uncheck this. And if you look at the network configurations for this, the IP address, you can see the IP address for this network on my laptop, which is 192.168.56.1. And so that's the range that I should be using. Okay, so now that I have identified the host-only network, the next step is to attach these virtual machines to that particular network. So in order to do that, right-click on each of these virtual machines, click on Settings, and go into the Network section. We know that the adapter 1 already connects to the bridged network, which is good, and we actually need that for enabling internet connectivity for these VMs, because we're going to connect to the internet to download and install packages. And what we could do is utilize the second adapter, which is adapter 2, and enable that particular adapter and set the attached to option to host only adapter and select the network, which is VirtualBox host only Ethernet adapter, and that's what we're going to connect to. I will leave everything else as default, so I will leave it all to the default option. So I now have two adapters on my virtual machine, one to the bridged one bridged to my router, and the other which is a host only network adapter. I'm going to click on OK to confirm my changes. I'm going to duplicate the same changes on both the other virtual machines. Okay, so I've made the changes on all the three VMs, and now I'm going to power them up. Okay, so all my virtual machines are now powered up. I'm going to open up a terminal on my master, and now when I run the ifconfig command, I can now see that there's a new interface which is actually called ENP0S8, and that's the new interface that was created, which is attached to the host-only network. As you can see, it doesn't have any IP address assigned to it. So what we're going to do is, there are two ways to assign an IP address. One is I could simply use the ifconfig command, specify the interface, which is ENP0S8, and assign an IP using this command. So just set the IP address. I'm not the root user, so I'm just going to switch to the root user, and I'm going to attempt to run that command again. So that's ifconfig enp0s8 192.168.56.2. So this actually does the trick. It assigns the IP address to my interface, and I will be able to access this virtual machine using this IP address. However, this is only temporary. As soon as you reboot your virtual machine, this IP is lost. So this is a temporary way of assigning an IP to the virtual machine. So this is not what we want. We need another way to assign a permanent way to assign an IP address to the virtual machine. So in order to do that, we need to go into the etc network interfaces file. So we need to edit this file and add the IP address to be assigned to this network into this file. So as you can see, this file already has an entry for the LO interface, which is the loopback interface. We're going to add a new line, a set of new lines to configure the new interface for the host-only network. And so we're going to the first line of entry is going to be auto enp0s8. And what this does is it automatically enables or turns on this particular interface when the operating system boots up. So we want it to automatically come up every time we boot up. The next line says iphase enp0s8 inet static. So that indicates that this particular interface has a static IP address, and then in the next line I'm going to specify that address, which is 192.168.56.2, and on the next line I'm going to specify the net mask, which is 255.255.255.0, and that's it. That's all I need to do. I'm going to now save this file, and I'm just going to reboot. This way, when it comes back up, it should automatically have had that IP address set, that network interface enabled, and IP address set. I'm going to duplicate what I did on my other virtual machine. So I'm going to go into KubeNode 1. I will edit the network interfaces file, and I'm going to use the same set of lines I used on the previous one, except for the IP address, of course, which is now going to be set to 192.168.56.3. And the net mask is going to remain the same. And I will save that file and reboot the host. And I will do the same with my second worker, which is KubeNode 2. I will modify the etc network interfaces file and add a new entry with a new address. which is going to be 192.168.56.4, and I'm going to reboot that system. Okay, and now I'll wait for all the systems to come back online. They're now back up, and I'm going to go into the terminal for my master. And there's one more thing that we need to verify to make sure that everything is set up properly. You need to make sure that you have internet connectivity. So what I'm going to do is I'm going to open up a terminal, and I'm going to ping an external website like google.com, and I need to make sure that I receive a response. Okay, so the last thing that I need to do is disable swap. So as it says, you must disable swap in order for kubelet to work properly, and that's what I'm going to do next. So I'm going to go on each of my system, and I need to do two things to make switch off or disable swap. The first is run a command swap off -a, and then the next step is to go into the etc fstab file and comment the line out for the swap, which is the bottom line on this file. So I'm going to add a hash in front of that line to comment it out. This way, when I restart or reboot my virtual machine, it doesn't automatically enable swap. Okay, so that's it. We're done with all of our prerequisites that are necessary to install and get started with the kubeadmin tool. We're now ready to use the kubeadmin tool to initialize a Kubernetes cluster. Well, thank you very much for your time, and I will see you in the next demo. Hello and welcome to this demo. In this demo, we're going to see how to use kubeadmin tool to set up a Kubernetes cluster. In the previous demo, we saw how to set up the VMs and prerequisites, and in this demo, we're going to see how to install the kubeadmin tool itself to set up the Kubernetes cluster. So if you look at the documentation page, as you can see, the next step is to install Docker. So we've gone through the prerequisites, and if you look at the steps that we have outlined here, we have the first step, which is identifying the master and worker nodes and configuring the prerequisites on those nodes, which is done. And the second step is to install Docker on all the nodes. That's what we're going to do next, followed by the third, fourth, fifth, and sixth steps. Now, if you look at the documentation here, that provides you with instructions on installing Docker on an Ubuntu system, it need not necessarily install the latest version of Docker, the latest and the supported version of Docker on your system if you follow this instruction. So it is always better to refer to the official Docker installation guide, and there's a link that is provided here. So if you go to the link, it takes you directly to the Get Docker website, and here under Linux you can select Ubuntu. So since I'm on Ubuntu, I'm going to select Ubuntu, and if you scroll down, you have instructions here to install Docker. So I'm going to start with the first one, which is setting up the repository. First, I'm going to update my repository index. So I'm going to run the sudo apt-get update command, and I'm going to run that on all the 3 nodes. While we wait for that to finish, the next step is to install the packages to allow apt to use the repository over HTTPS. I'm going to copy that section of command and run that once the apt-get update command is finished. And I'm going to run that command on all the 3 nodes. Okay, and while we wait for that to finish, the next step is to add the Docker's official GPG key. So once this command is completed, we're going to run that.
Okay, so that's added successfully on the master node, and we're going to repeat the same on the other two nodes. Okay, now I have successfully added the key on all the three nodes. And you can optionally verify if the key is added successfully following the next step, but for now I'm going to skip that. In the next step, I'm going to set up a stable repository for installing Docker on my Ubuntu system. So I'm going to run the add apt repository command on all the nodes. Once that is done, the next step is to install Docker. For this, first we're going to run the apt get update command on all the three nodes since we have added a new repository. And once that is completed, we're now going to run the next step is to install Docker using the apt get install command. Now here we need to make sure that we don't install the latest version. So if you follow the instruction on step 2, where you run the apt get install docker-ce command, you're actually going to install the latest version of Docker, but we don't actually want that. We would like to install a supported version of Docker. To find the supported version of Docker with Kubernetes, go to the Kubernetes documentation page under changelog and search for Docker version, and you'll see the supported Docker version. In this case, we see that it is 17.03. So that's what we need to install. So we're going to go to step 3, where we have the instruction to install a specific version of Docker. We're going to first run the command apt cache madison docker-ce, and it gives us a list of Docker versions that we can install. And then we're going to we have identified that it is 17.03 that we need to install. So we're going to use the command on the next step, which is apt get install docker-ce equals, and then we're going to provide the version of Docker we would like to install, which in this case is 17.03.2. We'll copy the same command and run it on the other two nodes. And we'll wait for that to finish. Once the installation is complete, we will run the docker version command to verify that the installed version is 17.03. And we'll do that on all three nodes.
Okay, so that's done. The next step is to install kubeadmin. As you can see, step 3 is to install kubeadmin as well as the other tools, which are kubelet and kubecontrol. So we're going to install all of these in one shot, and we will do that by following these steps that are written here. So the first step is to install the apt transport https package, which is a prerequisite. So I'm going to run that command on all the nodes. Okay, so that's completed on the kube master, and I'm going to run that on the other nodes right now. Okay, so I'm just going to clear the screen, and the next step is to download a particular key file, and I'm going to use curl for that, as the documentation says. And once I have installed curl, I'm going to run the command, and it says OK, which is good. I'm going to do the same on the other node, and I'm going to do the same thing on node 2. Okay, so that's successful on all the three nodes. Just going to clear my screen. The next step is to add the sources list
into my sources.list directory. So I'm going to copy that whole section and paste that. So what it basically does is it adds an entry to the particular file under sources.list and then updates the repository using the apt-get update command. Okay, so that's done as well. And so now the last step is to install the kubelet and other tools using the apt-get install command. So I'm going to run that on all the nodes. I'll now wait for that to finish. Okay, so that's finished, and the tools are now set up on all the nodes. Alright, so step 4 is to initialize a cluster. So we're going to scroll down, and if you click on under what's next, you have the link to go to the using kubeadmin to create a cluster page. And right here, if you scroll down, you see the list of instructions that are required to configure a Kubernetes cluster. So if you read through all the prerequisites, we've actually covered all of this already. So I'm just going to skip through that. The first step is to install kubeadmin, which we have actually done, so I'm going to skip that. And we're actually at step 2 out of 4 here, which is initializing the master. And that is actually step 4 in our list. So the idea is to run kubeadmin init command, but before you run that, go through the nodes and look at a few of these. So if you look at the second point under the nodes section, you can actually see that it says you need to choose a pod network plugin in the next step. So before we run the kubeadmin init command, we actually need to make that choice of the pod network plugin and specify some additional parameters with the kubeadmin init command. So we'll check the first one, which is to provide the pod network plugin parameter. So if you scroll down to the next step before running the kubeadmin init command, and if you look at step 3, which is installing a pod network, this is actually to be done after we initialize the master. But before we initialize the master, we have to make a choice as to which network we're going to use. So if you remember that we discussed in the lecture, there are multiple pre-built solutions available for networking, and at this stage we need to make a choice of choosing one. I usually use Calico or Flannel for my local VM setup, so you could go with any of these. As you can see in the note here, in order for network policy to work correctly, you need to pass the pod network CIDR parameter to the kubeadmin init command. So what we're going to do is we're going to copy the parameter that's provided here, and I'm just going to copy it as it is. I'm going to pass it to my kubeadmin init command. So that's my first set of parameters that I'm going to pass to the kubeadmin init command. And if I now scroll back up, if you look at the second or third point under nodes, you see that you also have to specify the API server advertised address. The reason for this is, if you remember, on our virtual machines we now have 2 IP addresses or 2 or more IP addresses are on our virtual machines. The one with the 192.168.1 series is for the bridge adapter to my Wi-Fi network, and we created another one which is a host only one for the static IP address. So I actually have a dynamic IP and a static IP for my virtual machines. Now the reason we created the static IP was for the internal communication between the nodes in the cluster. When we initialize a Kubernetes master using the kubeadmin init command, it actually configures the master API server to listen to a particular interface. And so here we need to specify what interface or what IP address the master should listen to. We need to make sure that we don't actually listen on the dynamic IP. Instead, we listen on the static IP address. So I'm going to copy this particular option of API server advertise address, and I'm going to place that here, and I'm going to set that particular IP address to 192.168.56.2 because that's the static IP address I assigned to my Kubernetes master node. So remember to use the static IP address here. When I run, it actually goes ahead and performs a lot of steps required to initialize the master, to install all the required components on the master node, and configures Kubernetes master and initializes master to listen on a particular IP address. Okay, as you can see, it says Kubernetes master has initialized successfully, which is great, and there are a few other instructions available for us to get started with it. The first few being there are a few instructions for the non-root user. And it also says that you can make a record of the kubeadmin join command that is part of the output. This is so we can use that later while on the worker nodes while joining to the master. So I'm just going to copy that, and I'm going to save that temporarily in a notepad. Okay, so if you scroll down, the next step is installing a pod network. So a pod network is required for internal communication between the worker nodes and the master. And we will actually go through this pod networking in much more detail later during the networking section. So for now, we're just going to follow the step as is to get it set up. And it's actually easy to set up this particular networking. All you need to do is copy this line of command that's available here and execute that on our master node. And when we actually do that, what it's doing underneath this is actually spinning up a set of Kubernetes services to set up internal networking. If you read here, it says once a pod network has been installed, you can confirm that it is working by checking that the kubedns pod is running in the output of the kubecontrol get pods all namespaces. So if you copy the kubecontrol get pods all namespaces command and execute that, you'll actually see a set of services that are being spun up by Kubernetes. And if you see there's one called kubedns, make sure that it is in a running state. It may take a few minutes for this to come up, so you'll just have to wait and give it some time. As you can see, it's running, so we are good. So the next step and the final step is to join the worker nodes, the master node, and this is where we will utilize the command that we saved. So I'm going to open up my notepad where I saved the command, the kubeadmin join command, and I'm going to run that command on my worker nodes. And as you can see, it comes back with a message that says successfully established connection with the API server. That's a good sign. And I'm going to run that on both the nodes. And once I do that, get the command kubecontrol get nodes and run it on my master. And when I run it on my master, I should be able to see the two other nodes that are listed here. In this case, the second node is not ready yet, so we'll just give it some time. And when you run the command again, you can see that it is now in a ready state. You could now test a deployment by running the kubecontrol run nginx command, and there you can actually see that it's created successfully and it's actually running a pod, which is a good sign. So that's it for this demo. In this demo, we set up a Kubernetes cluster using the kubeadmin tool, and we ensured that the communication between the master and the worker nodes is successful and the nodes joined the cluster successfully. That's it for this demo. Thank you for your time, and I will see you in the next lecture. Hello and welcome to this demo. In this demo, we're going to look at deploying our application on Google Container Engine or Kubernetes Engine on Google Cloud Platform. We will first start with setting up our Google Container Engine platform. So let's get started. Okay, so here I have my Google Cloud console. I'm logged into my Google Cloud Platform with a test account. And this is my dashboard. We will now look at what Kubernetes Engine is. So if you look at the documentation page for Kubernetes Engine, you can see that it's a managed environment for deploying containerized applications on Google Cloud Platform. You can see its various features on this page. And so this is basically a pre-configured Kubernetes cluster that you can get on Google Cloud Platform with a single click. If you scroll down to the bottom, you will see a link to a quick start, and if you go in here, you will see basic information on how to get started with Kubernetes on Google Cloud Platform. So we're going to follow these instructions. So I'm logged into my Google Cloud Platform console, and when I go into the menu on the left, I have Kubernetes Engine on the left, so I'm going to click on that. And this takes me to the Kubernetes dashboard. So I do not have any cluster for now, so I'm going to click on Create a Cluster. And this brings up the form to create a cluster. So I'm going to give a name, example voting app. Just going to add a description. It is a Kubernetes cluster to deploy our example voting application. I will leave everything else as is at the default, and I'm going to click on create. So what this does is it basically creates a Kubernetes master node and 3 worker nodes, and take me to, and that's going to take a few minutes to deploy. And once it's ready, I will see a green check mark. Now, I just clicked on the Google Cloud Shell in the top right corner. What this is this gives me a temporary shell that I can work with. So it is in this shell that I'll be running all my Kubernetes commands. Now, it takes a few minutes for the cluster to be set up. So what I'm going to do for now is I'm going to click on the connect button on the example voting app cluster, and it gives me instructions on how to connect to my Kubernetes cluster. So in my Google Cloud Shell, I could run this command which is tcloud container clusters get credentials. I could run the command to get the credentials to connect to my Kubernetes cluster, and then once that command runs successfully, I will then be able to use the kubectl command line to interact with my Kubernetes cluster. So I'm going to copy the command and I will run it. I'm not sure if it's going to work because the cluster has not fully been set up yet. And yes, as you can see, it gives me a warning that states the cluster is still not running. So I'm going to wait for the cluster to start up. And yes, as you can see, I now have a green check mark next to the example voting app, and that indicates that the cluster is fully set up. So I'm going to rerun the command again, and as you can see, it says the kubeconfig is configured correctly. I should now be able to run kubectl commands on my Kubernetes cluster from this terminal. I'm going to run the kubectl get nodes command to get a list of nodes available in my cluster. As you can see, there are 3 nodes available and they're all in ready state. And I could run the kubectl get pods command to see a list of pods, and since I haven't created any pods, I do not see any. And I could run the kubectl get services command to get a list of services. But as you can see, there's one service already created, and that's a default service created by Kubernetes. So we can leave that at that. So I now have my Kubernetes cluster ready on Google Cloud Platform. Hello and welcome to this demo. In this demo, we're going to look at setting up a Kubernetes test environment on playwithk8s.com. So if you want to quickly play around with Kubernetes and you don't have enough time to set up your own environment, or you don't have an account on any public cloud provider or something, you can easily set up a very simple test environment on a solution called as playwithk8s.com. So in this demo, that is what we're going to look at. So if you go to play-with-k8s.com, we'll come to this site where you have access to a free set of Kubernetes cluster that you can easily play around with. So you have to click on I am not a robot. Once you're in, you can see this timer. So your sessions are only available for 4 hours. So you cannot persist your work in this environment. But if this is something that you want to quickly try on, something you want to really test or play around with, this is the best option for a limited period of time. So once you're in, to get an instance, click on Add New Instance. Okay, so it quickly provisions an instance, and you can see information about your instance right here. And look here, you can see some basic information available to get started. So you need to follow these 3 steps, or the first 2 at least, to set up your cluster. So I'm going to run the first command. I'm just going to copy the first command and run that. And this will initialize our cluster. Okay, so the master node is initialized and ready. The next step, if you go back to the top, is to initialize the cluster networking. So I'm going to copy this 2 lines of command and paste that and run that. Okay, so that's done, and it's initialized the cluster networking. The third is optional, so we're just going to skip that for now. So I'm now ready with my Kubernetes cluster. So I'm going to clear my screen, and I'm now all set to deploy my application on this cluster. That's all for this demo. I hope you enjoyed it. Thank you very much for your time, and I will see you in the next lecture.
Hello and welcome to this lecture on Kubernetes pods. My name is Mumshad Manambeth and we are learning Kubernetes for beginners. In this lecture, we will discuss about Kubernetes pods. Before we head into understanding pods, we would like to assume that the following have been set up already. At this point, we assume that the application is already developed and built into Docker images, and it is available on a Docker repository like Docker Hub, so Kubernetes can pull it down. We also assume that the Kubernetes cluster has already been set up and is working. This could be a single node setup or a multi-node setup, doesn't matter. All the services need to be in a running state. As we discussed before, with Kubernetes, our ultimate aim is to deploy our application in the form of containers on a set of machines that are configured as worker nodes in a cluster. However, Kubernetes does not deploy containers directly on the worker nodes. The containers are encapsulated into a Kubernetes object known as pods. A pod is a single instance of an application. A pod is the smallest object that you can create in Kubernetes. Here we see the simplest of simplest cases where you have a single node Kubernetes cluster with a single instance of your application running in a single Docker container encapsulated in a pod. What if the number of users accessing your application increase and you need to scale your application?
you need to add additional instances of your web application to share the load. Now, where would you spin up additional instances? Do we bring up new container instance within the same pod? No. We create new pod altogether with a new instance of the same application. As you can see, we now have two instances of our web application running on two separate pods on the same Kubernetes system or node. What if the user base further increases and your current node has no sufficient capacity? Well, then you can always deploy additional pods on a new node in the cluster. You will have a new node added to the cluster to expand the cluster's physical capacity. So what I'm trying to illustrate in this slide is that pods usually have a one-to-one relationship with containers running your application. To scale up, you create new pods, and to scale down, you delete existing pod. You do not add additional containers to an existing pod to scale your application. Also, if you're wondering how we implement all of this and how we achieve load balancing between the containers, etc., we will get into all of that in a later lecture. For now, we are only trying to understand the basic concepts. We just said that pods usually have a one-to-one relationship with the containers. But are we restricted to having a single container in a single pod? No. A single pod can have multiple containers except for the fact that they're usually not multiple containers of the same kind. As we discussed in the previous slide, if our intention was to scale our application, then we would need to create additional pods. But sometimes you might have a scenario where you have a helper container that might be doing some kind of supporting task for our web application, such as processing a user-entered data, processing a file uploaded by the user, etc. And you want these helper containers to live alongside your application container. In that case, you can have both of these containers part of the same pod, so that when a new application container is created, the helper is also created, and when it dies, the helper also dies since they are part of the same pod. The two containers can also communicate with each other directly by referring to each other as localhost, since they share the same network space. Plus, they can easily share the same storage space as well. If you still have doubts in this topic, I would understand if you did, because I did the first time I learned these concepts. We could take another shot at understanding pods from a different angle. Let's, for a moment, keep Kubernetes out of our discussion and talk about simple Docker containers. Let's assume we were developing a process or a script to deploy our application on a Docker host. Then we would first simply deploy our application using a simple docker run Python app command, and the application runs fine and our users are able to access it. When the load increases, we deploy more instances of our application by running the docker run commands many more times. This works fine and we're all happy. Now, sometime in the future, our application is further developed, undergoes architectural changes, and grows and gets complex. We now have a new helper container that helps our web application by processing or fetching data from elsewhere. These helper containers maintain a one-to-one relationship with our application container and thus needs to communicate with the application containers directly and access data from those containers. For this, we need to maintain a map of what app and helper containers are connected to each other. We would need to establish network connectivity between these containers ourselves using links and custom networks. We would need to create shareable volumes and share it among the containers. We would need to maintain a map of that as well. And most importantly, we would need to monitor the state of the application container, and when it dies, manually kill the helper container as well, as it's no longer required. When a new container is deployed, we would need to deploy the new helper container as well. With pods, Kubernetes does all of this for us automatically. We just need to define what containers a pod consists of,
and the containers in a pod by default will have access to the same storage, the same network namespace, and same fate, as in they will be created together and destroyed together. Even if our application didn't happen to be so complex and we could live with a single container, Kubernetes still requires you to create pods. But this is good in the long run, as your application is now equipped for architectural changes and scale in the future. However, also note that multi-pod containers are a rare use case, and we're going to stick to single containers per pod in this course. Let us now look at how to deploy pods. Earlier we learned about the kubectl run command. What this command really does is, it deploys a Docker container by creating a pod. So it first creates a pod automatically and deploys an instance of the nginx Docker image. But where does it get the application image from? For that, you need to specify the image name using the -- image parameter. The application image, in this case the nginx image, is downloaded from the Docker Hub repository. Docker Hub, as we discussed, is a public repository where latest Docker images of various applications are stored. You could configure Kubernetes to pull the image from the public Docker Hub or a private repository within the organization. Now that we have a pod created, how do we see the list of pods available? The kubectl get pods command helps us see the list of pods in our cluster. In this case, we see the pod is in a container creating state and soon changes to a running state when it is actually running. Also remember that we haven't really talked about the concepts on how a user can access the nginx web server. And so in the current state, we haven't made the web server accessible to external users. You can, however, access it internally from the node. For now, we will just see how to deploy a pod, and in a later lecture, once we learn about networking and services, we will get to know how to make this service accessible to end users. That's it for this lecture. We will now head over to a demo, and I will see you in the next lecture. Hello and welcome to this demo. In this demo, we're going to look at pods in Kubernetes. So here I have my Kubernetes cluster set up. I have a master and 2 worker nodes. And on my master node, I'm going to deploy a pod. So before that, I'm going to check the status of my nodes by running the kubectl get nodes command. So I have 3 nodes, 1 master and 2 workers. And to deploy a pod, I could use the kubectl or kubectl run command with the nginx image. So I'm going to specify the name of my pod, which is going to be nginx, and the image that I'm going to use for my pod, for my Docker container, is also named as nginx. As you can see, it comes back with the message that deployment nginx has been created, so that's good. And if I now run the kubectl get pods command, I see that there's a pod, but it's currently in the state container running. If I run the same command again after a few seconds or minutes, I will be able to see that it's in a running state, so that's good. To get more information about the pod, I could run the kubectl describe pods command, and as you can see in the output, it lists detailed information about the pod. It tells you on which node or which worker it is running. So we know that we have 2 workers, kube node 1 and kube node 2. This pod is in fact running on kube node 2. And you can also see the nginx image, the name of the image that was used. If you scroll down, you'll see additional information such as a set of events that followed the creation of the pod. As you can see, there were actually a few warnings and failures where it failed to pull the nginx image from the Docker Hub registry, but it eventually pulled it off after a few tries. And you can actually see those information in the events. So if you run the kubectl get pods command with the -o wide parameter, then you will actually see 2 additional fields in the output, which was not available earlier.
you have an IP and a node field. The IP is the IP that is assigned to a pod, so each pod gets its own IP address in Kubernetes. We will discuss about IP addresses and pods and later on in the networking section of the course. We will discuss that in detail, but for now just remember that each pod gets its own IP address, its internal IP address. In this case it happens to be 10.244.2.14, and you can also see the node on which this particular pod is deployed, and that is kube node 2. Well, that's it for this demo, and we were able to successfully deploy a pod. In the later demos, we will see more about how this pod fits into other components of Kubernetes, such as replica sets, deployments, etc. Thank you for your time, and I will see you in the next lecture.
Hello and welcome to this lecture. In this lecture, we take a look at what YAML files are. If you are familiar with YAML already, feel free to skip this section and head over to the next section. If you have not worked with YAML in the past, I would highly recommend going through this because the rest of the course depends entirely on YAML. If you have worked with other data structure formats like XML or JSON, you should be able to easily pick it up. Don't worry if you haven't worked on any of these, you should still be able to easily pick it up going through the coding exercises that accompany this course. A YAML file is used to represent data, in this case configuration data. Here is a quick comparison of a sample data in 3 different formats. The one on the left is XML, where we display a list of servers and their information. The same data is represented in JSON format in the middle, and finally in YAML format to the right. Take a minute to compare the 3 formats. Let's take a close look at YAML. If you take the data in its simplest form, such as key-value pair, this is how you would define it in YAML. Key and value separated by a colon. The keys are fruit, vegetable, liquid, and meat, and the values are apple, carrot, water, and chicken. Remember, you must have a space followed by a colon differentiating the key and the value. Let's take a look at how an array is represented. We would like to list some fruits and vegetables. We would say fruits followed by a colon. On the next line, enter each item with a dash in the front. The dash indicates that it's an element of an array. How about a dictionary? A dictionary is a set of properties grouped together under an item. Here we try to represent nutrition information of 2 fruits. The calories, fat, and carbs are different for each fruit. Notice the blank space before each item. You must have equal number of blank spaces before the properties of a single item, so they are all aligned together. Let's take a closer look at spaces in YAML. Here we have a dictionary representing the nutrition information of banana. The total amount of calories, fat, and carbs are shown. Notice the number of spaces before each property that indicates these key value pairs fall within banana. But what if we had extra spaces for fat and carbs? Then they will fall under calories and thus become properties of calories, which doesn't make any sense. This will result in a syntax error which will tell you that mapping values are not allowed here because calories already have a value set which is 105. You can either set a direct value or a hash map. You cannot have both. So the number of spaces before each property is key in YAML. You must ensure they're in the right form to represent your data correctly. Let's take it to another level. You can have lists containing dictionaries containing lists. In this case, I have a list of fruits, and the elements of the list are banana and grape. But each of these elements are further dictionaries containing nutrition information. A lot of students new to YAML have reached out to me asking when to use a dictionary or a list. So let me explain this a little bit better. First of all, it is important to understand that all of what we discussed so far, such as XML, JSON, or YAML, are used to represent data. It could be data about an organization and all of its employees and their personal details, or it could be data about a school and all of its students and their grades, or it could be data about an automobile manufacturing company and all of its cars and its details. It could be anything. Let's take an example of a car. A car is a single object, and it has properties such as color, model, transition, and price. To store different information or properties of a single object, we use a dictionary. In this simple dictionary, I have properties of the car defined in a key value format. This need not be as simple as this. For example, in case we need to split the model further into model name and make year, you could then represent this as a dictionary within another dictionary. In this case, the single value of model is now replaced by a small dictionary with two properties, name and year. So this is a dictionary within another dictionary. Let's say we would like to store the name of 6 cars. The names are formed by the color and the model of the car. To store this, we would use a list or an array, as it is multiple items of the same type of object. Since we are only storing the names, we have a simple list of strings. What if we would like to store all information about each car? Everything that we listed before, such as the color, model, transition, and price. We will then modify the array from a list of strings to a list of dictionaries. So we expand each item in the array and replace the name with the dictionary we built earlier. This way, we are able to represent all information about multiple cars in a single YAML file using a list of dictionaries. So that's the difference between dictionary, list, and list of dictionaries. I hope you understood the difference between the three and when to use each of these. Before we head over to exercises, let's take a look at some key notes. Dictionary is an unordered collection, whereas lists are ordered collection. So what does that mean? The two dictionaries that you see here have the same properties for banana. However, you can see that the order of properties, fat and carbs, do not match. In the first dictionary, fat is defined before carbs, and in the second dictionary, carbs comes first, followed by fat. But that doesn't really matter. The properties can be defined in any order, but the two dictionaries will still be the same as long as the values of each property match. This is not the same for lists or arrays. Arrays are ordered collection, so the order of items matter. The two lists shown are not the same because apple and banana are at different positions. This is something to keep in mind while working with data structures. Also remember, any line beginning with a hash is automatically ignored and considered as a comment. We are now ready to head over to the coding exercises and have fun playing with YAML files. Before heading into exercises, let me give you a brief idea on how the coding exercises work in this course. And this is the same way it works for the rest of the course, so it's good to have an idea on how to work with the coding exercises. So at the end of this video, on clicking the continue button, you will be automatically taken to the coding exercises section.
The coding exercises section, as you can see, consists of 3 different parts. The area at the top here is where your question is. This is where you are given instructions on your task. On the left side here, you can see 2 different files. You will always see 2 or more files here. The first and the default file is called exercise.rb. This file is never used, so you can see a temporary banner put here. We never actually use this file. If you look at the note here, you can see that this file is not used. Do not type in your solution in this file, and you must always use the adjacent .yaml or .txt file. So we will be working with 2 types of files. One is the .txt file for which we will use for inventory, Ansible inventory files. The other is the .yaml file, which is what we will be working with most of the time, and that is the Ansible playbook files. So never write anything into the exercise.rb. Switch over to the food.yaml file in this case, and if you look at the instructions, you can see that the instruction is to update food.yaml file to add a vegetable carrot. So there are currently 3 types already. So create a new entry here called vegetable and enter the name of the vegetable, in this case carrot. Now if you look at the bottom right corner, you will see there are 2 buttons. Click on the check solution button and it will check for your answer, and you must ensure that your answer is right. In this case I got an error because I typed in the spelling for vegetable wrong, so I'm going to correct that. Click on it again and you should see that your solution is correct. So you can then click on the continue button to go over to the second exercise. So this way you can go over all exercises until they're complete. And if you have any questions about any of these exercises, or if you find any issues with any of these exercises, feel free to reach out to me. Click on the browse Q&A button and then click on the ask a new question button to ask a new question, and I will make sure to reply to it as soon as possible. So go through the exercises, let me know what you think. So good luck.
Hello and welcome to this lecture. My name is Mumshad Manambeth and we are learning Kubernetes for beginners. In this lecture, we will talk about creating a pod using a YAML-based configuration file. In the previous lecture, we learned about YAML files in general. Now we will learn how to develop YAML files specifically for Kubernetes. Kubernetes uses YAML files as inputs for the creation of objects such as pods, replicas, deployments, services, etc. All of these follow a similar structure. A Kubernetes definition file always contains 4 top-level fields: the API version, kind, metadata, and spec. These are the top-level or root-level properties. These are also required fields, so you must have them in your configuration file. Let us look at each one of them. The first one is the API version. This is the version of the Kubernetes API we are using to create the object. Depending on what we are trying to create, we must use the right API version. For now, since we are working on pods, we will set the API version as v1. Few other possible values for this field are apps/v1 beta, extensions /v1 beta, etc. We will see what these are for later in this course. Next is the kind. The kind refers to the type of object we are trying to create, which in this case happens to be a pod. So we will set it as pod. Some other possible values here could be replica set or deployment or service, which is what you see in the kind field in the table on the right. The next is metadata. The metadata is data about the object, like its name, labels, etc. As you can see, unlike the first 2 where you have specified a string value, this is in the form of a dictionary.
So everything under metadata is intended to the right a little bit, and so names and labels are children of metadata. The number of spaces before the two properties, name and labels, doesn't matter, but they should be the same as they are siblings. In this case, labels has more spaces on the left than name, and so it is now a child of the name property instead of a sibling, which is incorrect. Also, the two properties must have more spaces than its parent, which is metadata, so that it's intended to the right a little bit. In this case, all three of them have the same number of spaces before them, and so they are all siblings, which is not correct. Under metadata, the name is a string value, so you can name your pod myapp_pod. And the labels is a dictionary, so labels is a dictionary within the metadata dictionary. And it can have any key and value pairs as you wish. For now, I have added a label app with the value myapp. Similarly, you could add other labels as you see fit, which will help you identify these objects at a later point in time. Say for example, there are hundreds of pods running a front-end application and hundreds of pods running a back-end application or a database. It will be difficult for you to group these pods once they are deployed. If you label them now as front-end, back-end or database, you will be able to filter the pods based on this label at a later point in time. It's important to note that under metadata, you can only specify name or labels or anything else that Kubernetes expects to be under metadata. You cannot add any other property as you wish under this. However, under labels, you can have any kind of key or value pairs as you see fit. So it's important to understand what each of these parameters expect. So far, we have only mentioned the type and name of the object we need to create, which happens to be a pod with the name myapp_pod. But we haven't really specified the container or image we need in the pod. The last section in the configuration file is the specification section, which is written as spec. Depending on the object we are going to create, this is where we would provide additional information to Kubernetes pertaining to that object. This is going to be different for different objects, so it's important to understand or refer to the documentation section to get the right format for each. Since we are only creating a pod with a single container in it, it is easy. Spec is a dictionary, so add a property under it called containers. Containers is a list or an array. The reason this property is a list is because the pods can have multiple containers within them, as we learned in the lecture earlier. In this case though, we will only add a single item in the list, since we plan to have only a single container in the pod. The dash right before the name indicates that this is the first item in the list. The item in the list is a dictionary, so add a name and image property. The value for image is nginx, which is the name of the Docker image in the Docker repository. Once the file is created, run the command kubectl create -f followed by the file name, which is poddefinition.yaml, and Kubernetes creates the pod. So to summarize, remember the 4 top-level properties: API version, kind, metadata, and spec. Then start by adding values to those depending on the object you are going to create. Once we create the pod, how do you see it? Use the kubectl getPods command to see a list of pods available. In this case, it's just one. To see detailed information about the pod, run the kubectl describe_pod command. This will tell you information about the pod, when it was created, what labels are assigned to it, what Docker containers are part of it, and the events associated with that pod. That's it for this lecture. We will now head over to a demo, and I will see you in the next lecture. Hello and welcome to this demo. In this demo, we're going to look at some tips and tricks on working with YAML files. Some of my students in the past have had issues getting the YAML files right, and sometimes it's hard to put together the YAML files for Kubernetes. So in this demo, we're going to look at some plugins that are available with PyCharm that will help us easily develop Kubernetes definition files. And we'll also look at how we can validate and ensure that the format of the YAML files that we develop is actually good. So let's get started. So JetBrains has a plugin for Kubernetes and OpenShift resource support. And if you go to plugins.jetbrains.com and search for Kubernetes, you'll actually find this. This is actually compatible with multiple JetBrains products like IntelliJ IDEA, WebStorm, PyCharm, etc. PyCharm is what we're using right now. And you can actually see the instructions that are available here on installing it, and you can see the different features that are available. So it has features for auto-completion of properties, resources, pop-up documentation of properties, etc. And this is actually going to help us very much. So to get it configured, you can actually download the latest version of the plugin that is available. So I've already downloaded it. It's in a zip format. And if you go into your PyCharm and if you go into File and Settings, you can actually install it from the plugins section of your settings. So select or click on the plugins section in settings, and there's an option called install plugin from disk. So I'm going to click on that and select the file that you downloaded. You can check the plugin there to enable it. So check it, click on OK, and it will ask you if you are ready to restart it. So you remember that you'll have to restart the IDE once you enable the plugin. So wait for it to come back up. And once it's back up, you can confirm that it's working by looking at any of your existing Kubernetes definition files. If it's working and if it's enabled properly, you will see that the icon of the file actually changes to the Kubernetes icon, which is the blue icon that you see there. So right now, I'm going to create the pod definition file again from scratch, just to show you how easy it is using this Kubernetes plugin to develop the configuration file. So I'm going to create a new empty file called pod definition 2.yaml. And as you can see, when it's blank, it doesn't actually identify it as a Kubernetes file because there's nothing in it. I'm now going to add the API version, the various root level properties of the document. So to start with the API version. Now when I type in API version, and after I have the colon in, and after the space, if I need to invoke the drop-down feature of Kubernetes plugin that I just installed, I could press the Control and Space combination key, and when I do that, it actually lists all the supported versions that are available, and the top one is V1, which is what we want. So I'm going to hit V1 and hit Enter. So it selects that value from the drop-down. And in the next line, I'm going to specify kind, and then again I'm going to hit the Control Space combination, and it lists me all the values that are available for V1. So right there it actually does a filter of all the types of objects that I can create in Kubernetes, filtered by the version that is specified in the previous line. So that's pretty cool. So even if you were trying to create say something else like a deployment and you didn't actually get your API version right, this will actually ensure that you get it right because it doesn't even list deployment here. So in our case, since we need to create a pod, it's actually listed here as it's part of V1, so we're good with that. So I'm going to select pod. Okay, and the next section is metadata. So as soon as I type meta, it automatically fills the remaining portion of it. It knows that it's an object, so it takes me to the next line and automatically intends it to a bit to the right. I can now add name, and as soon as I start typing something, it automatically populates the supported values. So I'm going to add label, and when I select label, it knows that it's a dictionary, so it automatically takes me to the next line and to the next level. And when I try to list suggestions at this level by pressing the control space combination, it says no suggestions. Now what that means is that as we discussed earlier, under labels I could actually have any key value pair as I want, because it's a set of labels and I could have any labels I want. So that's why it says no suggestion. So whenever it says no suggestions, that just means you can simply create any key value pairs over there. Okay, and then now I'm going to add spec. Now under the spec section, if I'm not sure what falls under it for pod, I could do a control space and it lists me the various options available for a pod under the spec section. And at the top you can see it has containers, which is what we usually use for a pod. And if you look at it, it has two brackets that indicates that it is a list item. So when you select containers, it takes you to the next line and to the right, indicating that it's an object. In this case it happens to be a list. I'm now going to create the first item in the container. So I need to add a dash followed by a space, and then if I'm not sure what was under it, I could do a control space and it lists me and tells me that it's name. So I'm going to put the name. Again, I'm going to do a control space, and you can see that it has image and image per policy, a number of other options available under it, and I can pick the one that I want. Okay, so that is great, and as you can see, it's really easy for us to create and validate that our Kubernetes definition file is valid using the Kubernetes plugin in JetBrains. As and when we go forward, we'll see more use cases of this plugin, but that is it for now. I also want to show you another trick to validate that your YAML file is in a good state. In my previous courses, students have had issues in the structure of the YAML files. Sometimes you have additional spaces in places where it's not required, or your certain lines are not intended correctly, etc. If you want to validate that before you actually use your YAML file, you could use YAML linters. This is a sample YAML lint website, so it's at yamllint.com, and it's very simple. You have a text box where you could put in your pod definition.yaml file, or any YAML file that you create, and click on go, and it'll tell you if it's a good or a bad file. In this case it's a good file. I'm just going to simulate an error by putting an extra space in an unwanted position, and when I click on go, it actually tells you where the error is. It tells you where the error is on and on which line it is. So this is actually really helpful for beginners in working with YAML. It helps you validate your YAML file before you actually use it. And in the coding exercises that follow this course, I would highly recommend checking your YAML files in a linter like the one that we just saw. That's it for this lecture. Thank you very much, and I will see you in the next demo.
Hello and welcome to this lecture on Kubernetes controllers. My name is Mumshad Manambeth and we are learning Kubernetes for beginners. In this lecture, we will discuss about Kubernetes controllers. Controllers are the brain behind Kubernetes. They are the processes that monitor Kubernetes objects and respond accordingly. In this lecture, we will discuss about one controller in particular, and that is the replication controller. So, what is a replica and why do we need a replication controller?
Let's go back to our first scenario where we had a single pod running our application. What if for some reason our application crashes and the pod fails? Users will no longer be able to access our application. To prevent users from losing access to our application, we would like to have more than one instance or pod running at the same time. That way, if one fails, we still have our application running on the other one. The replication controller helps us run multiple instances of a single pod in the Kubernetes cluster, thus providing high availability. So does that mean you can't use a replication controller if you plan to have a single pod? No. Even if you have a single pod, the replication controller can help by automatically bringing up a new pod when the existing one fails. Thus, the replication controller ensures that the specified number of pods are running at all times, even if it's just 1 or 100. Another reason we need replication controller is to create multiple pods to share the load across them. For example, in this simple scenario, we have a single pod serving a set of users. When the number of users increase, we deploy additional pod to balance the load across the two pods. If the demand further increases and if we were to run out of resources on the first node, we could deploy additional pods across the other nodes in the cluster. As you can see, the replication controller spans across multiple nodes in the cluster. It helps us balance the load across multiple pods on different nodes as well as scale our application when the demand increases. It's important to note that there are two similar terms, replication controller and replica set. Both have the same purpose, but they're not the same. Replication controller is the older technology that is being replaced by replica set. Replica set is the new recommended way to set up replication. However, whatever we discussed in the previous few slides remain applicable to both these technologies. There are minor differences in the way each works, and we will look at that in a bit. As such, we will try to stick to replica sets in all of our demos and implementations going forward. Let us now look at how we create a replication controller. As with the previous lecture, we start by creating a replication controller definition file. We will name it rc-definition.yaml. As with any Kubernetes definition file, we have 4 sections: the API version, kind, metadata, and spec. The API version is specific to what we are creating. In this case, replication controller is supported in Kubernetes API version v1. So we will set it as v1. The kind, as we know, is replication controller. Under metadata, we will add a name and we will call it myapp-rc, and we will also add a few labels, app and type, and assign values to them. So far, it has been very similar to how we created a pod in the previous section. The next is the most crucial part of the definition file, and that is the specification written as spec. For any Kubernetes definition file, the spec section defines what's inside the object we are creating. In this case, we note that the replication controller creates multiple instances of a pod. But what pod? We create a template section under spec to provide a pod template to be used by the replication controller to create replicas. Now, how do we define the pod template? It's not that hard because we have already done that in the previous exercise. Remember, we created a pod definition file in the previous exercise. We could reuse the contents of the file to populate the template section. Move all the contents of the pod definition file into the template section of the replication controller, except for the first few lines, which are API version and kind. Remember, whatever we move must be under the template section, meaning they should be intended to the right and have more spaces before them than the template line itself. they should be children of the template section. Looking at our file now, we now have two metadata sections. One is for the replication controller and another for the pod, and we have two spec sections, one for each. We have nested two definition files together, the replication controller being the parent and the pod definition being the child. Now there is something still missing. We haven't mentioned how many replicas we need in the replication controller. For that, add another property to the spec called replicas and input the number of replicas you need under it. Remember that the template and replicas are direct children of spec sections, so they are siblings and must be on the same vertical line, which means having equal number of spaces before them. Once the file is ready, run the kubectl create command and input the file using the -f parameter. The replication controller is created. When the replication controller is created, it first creates the pods using the pod definition template, as many as required, which is 3 in this case. To view the list of created replication controllers, run the kubectl get replication controller command and you will see the replication controller listed. We can also see the desired number of replicas or pods, the current number of replicas, and how many of them are ready in the output. If you would like to see the pods that were created by the replication controller, run the kubectl get pods command and you will see 3 pods running. Note that all of them are starting with the name of the replication controller, which is myapp-rc, indicating that they are all created automatically by the replication controller. What we just saw was the replication controller. Let us now look at replica set. It is very similar to replication controller. As usual, first we have API version, kinds, metadata, and spec. The API version though is a bit different. It is apps/v1, which is different from what we had before for replication controller, which was just v1. If you get this wrong, you are likely to get an error that looks like this. It would say no match for kind replica set because the specified Kubernetes API version has no support for replica set. The kind would be replica set, and we add name and labels in the metadata. The specification section looks very similar to replication controller. It has a template section where we provide pod definition as before. So I'm going to copy contents over from pod definition file and we have number of replicas which is set to 3. However, there is one major difference between replication controller and replica set. Replica set requires a selector definition. The selector section helps the replica set identify what pods fall under it. But why would you have to specify what pods fall under it if you have provided the contents of the pod definition file itself in the template? It's because replica set can also manage pods that were not created as part of the replica set creation. Say for example, there were pods created before the creation of the replica set that matched labels specified in the selector. The replica set will also take those pods into consideration when creating the replicas. I will elaborate this in the next slide. But before we get into that, I would like to mention that the selector is one of the major differences between replication controller and replica set. The selector is not a required field in case of a replication controller, but it is still available. When you skip it, as we did in the previous slide, it assumes it to be the same as the labels provided in the pod definition file. In case of replica set, a user input is required for this property, and it has to be written in the form of match labels as shown here. The match labels selector simply matches the labels specified under it to the labels on the pod. The replica set selector also provides many other options for matching labels that were not available in a replication controller.
And as always, to create a replica set, run the kubectl create command, providing the definition file as input. And to see the created replicas, run the kubectl get replica set command. To get list of pods, simply run the kubectl get pods command. So what is the deal with labels and selectors? Why do we label our pods and objects in Kubernetes? Let us look at a simple scenario. Say we deployed 3 instances of our front-end web application as 3 pods. We would like to create a replication controller or replica set to ensure that we have 3 active pods at any time. And yes, that is one of the use case of replica sets. You can use it to monitor existing pods if you have them already created, as it is in this example. In case they were not created, the replica set will create them for you. The role of the replica set is to monitor the pods, and if any of them were to fail, deploy new ones. The replica set is in fact a process that monitors the pods. Now, how does the replica set know what pods to monitor? There could be hundreds of other pods in the cluster running different applications. This is where labeling our pods during creation comes in handy. We could now provide these labels as a filter for replica set. Under the selector section, we use the match labels filter and provide the same label that we used while creating the pods. This way, the replica set knows which pods to monitor. The same concept of labels and selectors is used in many other places throughout Kubernetes. Now let me ask you a question along the same lines. In the replica set specification section, we learned that there are 3 sections: template, replicas, and the selector. We need 3 replicas, and we have updated our selector based on our discussion in the previous slide. Say for instance, we have the same scenario as in the previous slide, where we have 3 existing pods that were created already, and we need to create a replica set to monitor the pods to ensure there are a minimum of 3 running at all times. When the replication controller is created, it is not going to deploy a new instance of pod, as 3 of them with matching labels are already created. In that case, do we really need to provide a template section in the replica set specification, since we are not expecting the replica set to create a new pod on deployment? Yes, we do, because in case one of the pods were to fail in the future, the replica set needs to create a new one to maintain the desired number of pods. And for the replica set to create a new pod, the template definition section is required. Let's now look at how we scale the replica set. Say we started with 3 replicas, and in the future we decided to scale to 6. How do we update our replica set to scale to 6 replicas? Well, there are multiple ways to do it. The first is to update the number of replicas in the definition file to 6. Then run the kubectl replace command to specify the same file using the -f parameter, and that will update the replica set to have 6 replicas. The second way to do it is to run the kubectl scale command, use the replicas parameter to provide the new number of replicas and specify the same file as input. You may either input the definition file or provide the replica set name in the type name format. However, remember that using the file name as input will not result in the number of replicas being updated automatically in the file. In other words, the number of replicas in the replica set's definition file will still be 3, even though you scaled your replica set to have 6 replicas using the kubectl scale command and the file as input. There are also options available for automatically scaling the replica set based on load, but that is an advanced topic and we will discuss it at a later time. Let us now review the commands real quick. The kubectl create command, as we know, is used to create a replica set. or basically any object in Kubernetes depending on the file we are providing as input. You must provide the input file using the -f parameter. Use the kubectl get command to see list of replica sets created. Use the kubectl delete replica set command followed by the name of the replica set to delete the replica set. And then we have the kubectl replace command to replace or update the replica set. And also the kubectl scale command to scale replica set simply from the command line without having to modify the file. That's it for this lecture. We will now head over to a demo and I will see you in the next lecture. Hello and welcome to this demo. In this demo, we're going to look at replica sets. In my project folder, I'm now going to create a new folder called replica set. And under that, I will now create a new definition file for my replica set, and I will name it as replica set-definition.yaml. In this file, I'm now going to create my file structure. So I will start with the API version. So now, if you're not sure about the file structure or the contents of a particular definition file, you may refer to the Kubernetes documentation site at kubernetes.io/docs. Under this, if you select the documentation section for a particular object, you will see examples and you will be able to pick up some templates from there. Now, as I see, it's apps/a1, that's the API version, and when I try to input the kind, it automatically gives me a list of objects available under the API version. And so I select replica set from the drop-down list. I now populate metadata. Under metadata, I'm going to set the name for my replica set as my app-replica set. And I will also add some labels to my replica set. The next is the spec section, which is the most crucial part of this definition file. Under spec, as you can see, I have template, so I will select template. Now under template, I have spec and metadata. As you can see, it is referring to the spec of the pod, which is what is shown here as v1.pod spec. Under spec of the replica set, I can also have replicas. And then if I hit Control space, it also lists me selectors. So I'm going to select that as well. Now, if I remove one of it, as you can see, there's a warning shown against spec. So this is the Kubernetes plugin for PyCharm that's giving me this warning, and it says that I am missing a required properties on the replica set spec. Now this is great because while I'm developing Kubernetes definition files, it would be nice if it gave me these kind of warnings where I am told if there is something that I'm missing or something out of place. So in this case, it tells me that the selector is a required property for replica set, as we discussed during the lecture, and so it picks that out. So I'm now going to add the selector back in. Okay, now under the template section, we could copy the contents of the pod definition file. I now have the pod definition file open on the right side. So now I'm going to copy the contents of it, except for the first two lines, which are the API version and kind, and I will place it under template. Now remember, I've added a tab after template because template is an object, and I'm now going to paste the contents that I copied under template. However, as soon as I do that, as you can see, there are a number of warnings and error messages shown. This is because when I copied the section from my pod definition file, all of the properties were at the root level of that file. And so when I pasted it here, some of these lines are not intended properly. The easy way to do it, instead of doing it line by line, which may lead to further confusion, the easier way to do it is to select all of those lines that I pasted except for the first line and hit the tab key twice, and that will move all of the selected lines to the right twice, and that way putting the lines under the template section as required. Now, as you can see, all the warnings and error messages have disappeared. The metadata section falls under template, and the specs section for the pod also falls under template. I will now update the number of replicas to 3. And finally, under selector, as you can see, there are 2 options available: match expressions and match labels. So I'm going to select match labels. And then I'm going to copy the labels from the pod definition and paste it under the match labels section. The selector is used to link the replica set with the pods. Okay, so now that I have the file completed, I'm going to copy the contents of the file. Before using it, I'm actually going to run a linked checker on it. So I will use the YAML linked website to check it, and it looks good. So the structure of the file looks good. So I'm going to copy it now. I'm now going to create the replica set definition.yaml file on my Kubernetes master node, and I will place the contents that I copied from my IDE. I will now verify the contents of the file. Okay, and that looks good. I will now create the replica set using the kube control create-f replica set definition.yaml file. Okay, there you go, and as you can see, the replica set has been created. I will now run the command kubecontrol get replica set to see the list of replica sets. In this case, I have a single replica set, and as you can see, the number of pods under it. The desired number is 3, the current number is 3, and the pods that are ready is 1. I will now run it again a few times. When I run the kubecontrol describe command, I can see additional information about my replica set. I can see the name of it, the selector, the labels assigned to it, and I can also see the pod template and the image used by the pod. In the events, you can see the list of different pods that were created as part of this replica set. When I run the kubecontrol get pods command, I can now see that there are 3 pods created and they're in a running state. They all have the name of the replica set prefixed to their names, and then there's a unique ID that separates the name of these pods. Okay, now to test my replica set, what I'm going to do is I'm now going to delete one of the pod, because as we discussed in the lecture, the replica set is supposed to monitor the pods, and if any of them goes down, it's supposed to bring them back automatically to meet the number of replicas that we specified in the definition file. Now, to test if the replica set is working properly, I'm going to delete one of the pod that I created, that was created under the replica set. And as you can see, when I now run the get pods command, you can see that one of the pods is terminating, which is the pod that I tried to delete. At the same time, it's created another pod which is in a container creating state. So one is in a terminating state and another is in a creating state, and in a few seconds the one that I deleted is completely gone, and there's a new one which is now in a running state. So the replica set has automatically brought up a new pod when it detected that one of the replicas is missing. Okay, let's try something else now. I'm going to go into the pod definition file that we created earlier, and I'm now going to create an additional pod. So as we know, a replica set monitors the number of pods and makes sure that the number of that it maintains the number of pods that we specified. When we deleted one, it automatically created a new one. But what happens when you try to create a new pod outside of the replica set? In this case, I'm just going to create a new pod directly, and as you can see, it's already in a terminating state, which means as soon as we created the pod, replica set noticed it and it deleted that or terminated that pod immediately. because it will not allow you to create new pods with the same labels. Now remember that this is only effective to the pods that are with the same labels that the replica set filter is set to. If you create a new pod with a different label, then that is going to continue to run, and it's not going to be under the radar of the replica set. When I run the kubectl describe replica set command, and when I look at the events, I can now see that the additional events created when a new container was created, and you can see the additional event created when a container was deleted when I tried to add a pod manually. Okay, now if I run the kubectl get pods command with a -o wide option, I can see two additional fields, IP and node. I can now see the distribution of my pods on the two different nodes. There are two pods running on node 1 and one running on node 2. I'm now going to make a change to my replica set. I'm going to update the number of replicas to 6 because I want to scale the number of pods. I will now go to my replica set definition file and update the replica set definition file with my new definition. Okay, now I'm going to run the kubectl replace command to update my replica set, and I will provide the replica set definition file as the input. When I now run the kubectl get replica set command, I can now see that the number of desired replicas is 6, and the number of current replicas is 6, and the number of them that are ready is 3. If I run the describe replica set command to see additional information under events, I can now see that 3 new replicas was created. If I now run the kubectl get pods command, I should be able to see all the replicas. However, there is one still under creation. When I now run it again, I see that it's in a running state. If I now run the kubectl get pods command with a wide option, I can now see that all the pods are distributed equally across the two nodes. There are 3 on node 1 and 3 on node 2. I can achieve the same by running the kubectl scale command, and now I'm going to scale down my replica set by using the kubectl scale command and with an option replicas equals 3. When I now run the kubectl get replica set command, I can see that the desired number of replicas is 3, and when I run the kubectl get pods command, I see that only 3 replicas are running. However, if you look at the replica set definition file, it still has the number of replicas set to 6. So remember that even if you use the file as input for the scale command, it doesn't automatically update the number of replicas inside the file. So watch out for that. I'm now going to delete my replica set by running the kubectl delete replica set command, and as you can see, the replica set is deleted. If I run the kubectl get all command to list all of the objects in my cluster, I see that there's one still pending and it should be gone anytime now. When I run it again, I see that it's gone and there's only the default Kubernetes service running. Well, that's it for this demo. Thank you for your time, and I will see you in the next demo.
Hello and welcome to this lecture. My name is Mumshad Manambeth and we are learning Kubernetes for beginners. In this lecture, we will discuss about Kubernetes deployments. For a minute, let us forget about pods and replica sets and other Kubernetes concepts and talk about how you might want to deploy your application in a production environment. Say for example, you have a web server that needs to be deployed in a production environment. You need not one, but many such instances of the web server running for obvious reasons. Secondly, whenever newer versions of application builds become available on the Docker registry, you would like to upgrade your Docker instances seamlessly. However, when you upgrade your instances, you do not want to upgrade all of them at once as we just did. This may impact users accessing our application, so you might want to upgrade them one after the other. And that kind of upgrade is known as rolling updates. Suppose one of the upgrades you performed resulted in an unexpected error and you're asked to undo the recent change. You would like to be able to roll back the changes that were recently carried out. Finally, say for example, you would like to make multiple changes to your environment, such as upgrading the underlying web server versions, as well as scaling your environment and also modifying the resource allocations, etc. You do not want to apply each change immediately after the command is run. Instead, you would like to apply a pause to your environment, make the changes, and then resume so that all the changes are rolled out together. All of these capabilities are available with the Kubernetes deployments. So far in this course, we discussed about pods, which deploy single instances of our application, such as the web application in this case. Each container is encapsulated in pods. Multiple such pods are deployed using replication controllers or replica sets. And then comes deployment, which is a Kubernetes object that comes higher in the hierarchy. The deployment provides us with the capability to upgrade the underlying instances seamlessly using rolling updates, undo changes, and pause and resume changes as required. So how do we create a deployment? As with the previous components, we first create a deployment definition file. The contents of the deployment definition file are exactly similar to the replica set definition file, except for the kind, which is now going to be deployment. If we walk through the contents of the file, it has an API version, which is apps/v1, metadata, which has name and labels, and a spec that has template, replicas, and selector. The template has a pod definition inside it. Once the file is ready, run the kubectl create command and specify the deployment definition file. Then run the kubectl get deployments command to see the newly created deployment. The deployment automatically creates a replica set, so if you run the kubectl get replica set command, you will be able to see a new replica set in the name of the deployment. The replica sets ultimately create pods, so if you run the kubectl get pods command, you will be able to see the pods with the name of the deployment and the replica set. So far, there hasn't been much of a difference between replica set and deployments, except for the fact that deployment created a new Kubernetes object called deployments. We will see how to take advantage of the deployment using the use cases we discussed in the previous slide in the upcoming lectures. And one more note before we end this lecture: to see all the created objects at once, run the kubectl get all command. And in this case, we can see that the deployment was created, and then we have the replica set followed by 3 pods that were created as part of the deployment. That's it for this lecture. We will now head over to a demo, and I will see you in the next lecture.
Hello and welcome to this demo. In this demo, we will be looking at deployments in Kubernetes. So here I have my Kubernetes master and 2 worker nodes. I'm now going to create a definition file for deployments. So I'm in my PyCharm IDE, and I'm now going to create a new folder for my deployment. I will call that deployment, and I will create a new file under it, and I will call that deployment-definition.yaml. Okay, so I have my deployment definition file here, and on the right I have the replica set definition file. So as we said in the lecture, the contents of both the files are very similar, so at least for our purposes. So I'm going to refer to that to create my deployment definition file. I'm first going to specify the API, and it is going to be apps/v1, and the kind is going to be deployment.
So I can see deployment from the drop down. Under metadata, I'm going to specify a name for my deployment. I will call it my app-deployment, and I'll have a label called app, my app, and a type called frontend. Now, the specs section for the deployment is very similar to the one we have in the Replica set, so I'm just going to copy the contents over from my Replica set definition file, and I will place it here. I'll just change the number of replicas to 3 to start with, and everything else remains the same. We have the template. Under template, we have the pod definition file contents, and we have a replicas, a number, and a selector. Now remember, in production use cases, typically you will not be creating a pod definition file or a replica set definition file. In most use cases, you will be creating only a deployment definition file directly. Now if you want to, you could start by creating a separate pod definition file and copy the contents from that over to the deployment definition file if you feel that that's more convenient for you, but that is not necessary. For any project, you could directly start by creating a deployment definition file. Now once I have the file created, I'm going to do a quick lint check. So I'm going to copy the contents over from the editor, and I will place it in the YAML lint website. I'll click on go and make sure that it's a valid YAML file. Okay, so now on my Kubernetes master node, under the demos folder, I will create a folder structure for my deployment definition file. So I will create a new folder named deployment, and under that I will create a deployment definition file and copy over the contents. Now to create the deployment, I will run the kubectl create command, and before that I just want to make sure there's nothing running already, so I'm just going to run a kubectl get all command, and as you can see, there's only a default service running, and so we're good. Now I'm going to run the kubectl create deployment definition command to create the deployment. And when I now run the kubectl get all command, I can see that it's created my deployment, and the deployment has in turn created the replica set, and the replica set has in turn created my pods. So I can see the 3 pods running my application, and I have the replica set and the deployment. To see more details about the deployment, run the kubectl describe deployment command, and you will see additional information about the deployment, the time that it was created, the labels that is specified, the selector, and the image that's under the pod template, and the status. Under the events, you can see that the deployment has scaled up replica set my app deployment to 3, and that's the only event. Well, that's it for this demo. We will see more operations on the deployment in the upcoming lecture, and we will see more demos on deployment in a short time. That's it for this demo, and I will see you in the next demo.
Hello and welcome to this lecture. In this lecture, we will talk about updates and rollbacks in a deployment. Before we look at how we upgrade our application, let's try to understand rollouts and versioning in a deployment. When you first create a deployment, it triggers a rollout. A new rollout creates a new deployment revision. Let's call it revision 1. In the future, when the application is upgraded, meaning when the container version is updated to a new one, a new rollout is triggered and a new deployment revision is created named revision 2. This helps us keep track of the changes made to our deployment and enables us to roll back to a previous version of deployment if necessary. You can see the status of your rollout by running the command kubectl rollout status followed by the name of the deployment. To see the revisions and history of rollout, run the kubectl rollout history command followed by the deployment name, and this will show you the revisions and history of our deployment. There are two types of deployment strategies. Say for example, you have 5 replicas of your web application instance deployed. One way to upgrade these to a newer version is to destroy all of these and then create newer versions of application instances. Meaning, first destroy the 5 running instances and then deploy 5 new instances of the new application version. The problem with this, as you can imagine, is that during the period after the older versions are down and before any newer version is up, the application is down and inaccessible to users. This strategy is known as the recreate strategy, and thankfully this is not the default deployment strategy. The second strategy is where we do not destroy all of them at once. Instead, we take down the older version and bring up a newer version one by one. This way the application never goes down and the upgrade is seamless. Remember, if you do not specify a strategy while creating the deployment, it will assume it to be rolling update. In other words, rolling update is the default deployment strategy. So we talked about upgrades. How exactly do you update your deployment? When I say update, it could be different things such as updating your application version by updating the version of Docker containers used, updating their labels, or updating the number of replicas, etc. Since we already have a deployment definition file, it is easy for us to modify this file. Once we make the necessary changes, we run the kubectl apply command to apply the changes. A new rollout is triggered and a new revision of the deployment is created. But there is another way to do the same thing. You could use the kubectl setImage command to update the image of your application. But remember, doing it this way will result in the deployment definition file having a different configuration. So you must be careful when using the same definition file to make changes in the future. The difference between the recreate and rolling update strategies can also be seen when you view the deployments in detail. Run the kubectl describe deployment command to see the detailed information regarding the deployments. You will notice when the recreate strategy was used, the events indicate that the old replica set was scaled down to 0 first, and then the new replica set scaled up to 5. However, when the rolling update strategy was used, the old replica set was scaled down one at a time, simultaneously scaling up the new replica set one at a time. Let's look at how a deployment performs an upgrade under the hood. When a new deployment is created, say to deploy 5 replicas, it first creates a replica set automatically, which in turn creates the number of pods required to meet the number of replicas. When you upgrade your application, as we saw in the previous slide, the Kubernetes deployment object creates a new replica set under the hood and starts deploying the containers there, at the same time taking down the pods in the old replica set following a rolling update strategy. This can be seen when you try to list the replica sets using the kubectl getReplicaSets command. Here we see the old replica set with 0 pods and the new replica set with 5 pods. Say for instance, once you upgrade your application, you realize something isn't very right. Something's wrong with the new version of build you used to upgrade. So you would like to roll back your update. Kubernetes deployments allow you to roll back to a previous revision. To undo a change, run the kubectl rollout undo command followed by the name of the deployment. The deployment will then destroy the pods in the new replica set and bring the older ones up in the old replica set, and your application is back to its older format. When you compare the output of the kubectl getReplicaSets command before and after the rollback, you will be able to notice this difference. Before the rollback, the first replica set had 0 pods and new replica set had 5 pods, and this is reversed after the rollback is finished. And finally, let's get back to one of the commands we ran initially when we learned about pods for the first time. We used the kubectl run command to create a pod. This command in fact creates a deployment and not just a pod. This is why the output of the command says deployment nginx created. This is another way of creating a deployment by only specifying the image name and not using a definition file. The required replica set and pods are automatically created in the backend. Using a definition file is recommended though, as you can save the file, check it into the code repository and modify it later as required. To summarize the commands real quick, use the kubectl create command to create the deployment, get deployments command to list the deployments, apply and set image commands to update the deployments, and rollout status command to see the status of rollouts, and rollout undo command to roll back a deployment operation. That's it for this lecture. We will now head over to a demo and I will see you in the next lecture.
Hello and welcome to this demo. In this demo, we're going to look at updates and rollbacks in deployments. I'm on the Kubernetes master node and I'm going to create a deployment using the kubectl create command. First, I'm going to see if there's anything existing by running the kubectl get all command. And as you can see, there's nothing running except for the default Kubernetes service, so that is fine. I'm now going to create a new deployment by running the kubectl create deployment command. As soon as I run the create command, I could run a kubectl rollout status command to see the status of the rollout. As we discussed in the lecture, whenever a new Kubernetes deployment is created or an existing deployment is upgraded, it creates a new rollout. And a rollout is the process of deploying the containers in the backend. As you can see, it deploys one at a time. So you have, as you can see, 2 of 6, 3 of 6, 4 of 6, etc. And finally, when it deploys all the 6 of 6, the deployment is considered to be successful. We also discussed that whenever a new rollout is created, a new deployment revision is created. So if you run the kubectl rollout history command, so I'm going to modify my previous command and change status to history, you can see that it's created one revision, that's revision number 1, but I do not actually see a change cause. That's the second column in the output. It says none. And that's because I did not ask Kubernetes to record the change that I made. In this case, it doesn't really matter because the first revision is usually created when we create the deployment initially. So what I'm going to do is I'm going to quickly delete the deployment by running the kubectl delete deployment command, just to do that again, but this time by asking Kubernetes to record the change. And as you can see, I'm just going to wait for all the objects to be deleted. When you run the kubectl delete command, it deletes all the deployment, the associated replica set, and the pods that were created as part of the deployment. So when I now run the kubectl get all command, you can see that it's all terminated and it's no longer seen. So that is good, everything is clean, and I can now recreate my deployment. So I'm going to run the same command, kubectl create, to create a new deployment, but this time I'm going to add a new flag called record --record. And what this really does is we're just going to first see the status of the rollout by running the kubectl rollout status command. and as you can see, it's deploying one pod at a time. We will wait for all the 6 pods to be deployed. Okay, so the deployment is successful. Now I'm going to run the history command to see the revisions. And now, as you can see, there's a revision 1 as earlier, but you can actually see the change cause, which is the same command that I ran to create the deployment by using the deployment definition file. Okay, so now I'm going to make a small change to my deployment. If you look at the Docker file or the Docker Hub page for my nginx image, you can see the versions. So here I'm using the image nginx, which means that I haven't really specified a tag or a version of the image. So by default, it assumes it to be latest, and in this case, the latest version is 1.13.9. So we are actually at the latest version. We need to simulate an upgrade or a downgrade of the deployment or just a change in our application. So what we're going to do is we're going to use a new version or a different version of the image. In this case, I'm going to go with 1.12, which is actually the previous version of the image. Now I just need to simulate a change in the image. It could be an upgrade or a downgrade you're doing. We'll just assume that it's an upgrade. But since we're already at the latest version, we do not have a newer image. So we're just going to use another version, which is 1.12, and assume that we're upgrading the my application. So now I've made a change to my image, and I'm going to apply that change by running the kubectl apply command with the deployment definition file. And as you can see, it says deployment, my app deployment configured, which is good. And I'm now going to run the kubectl rollout status command to see the status of my rollout. As I said, an upgrade also initiates a rollout. Since we have updated the image of our application, it has to go out and update the image on all the replica set. Okay, so the deployment is successful. As you can see, I now have 6 nodes that are up to date, and I can see all the pods. And if I do a describe deployment command to see the details, I can actually see the detailed image name or the new image, which is nginx 1.12. If you look at the events down below, you can actually see the events as it occurred. You can see that there are 2 replica sets mentioned here, of which one which is the older one, is scaled down one at a time, and at the same time the new replica set with the newer image is scaled up one at a time. So you can actually see the events. Okay, and now I'm going to see the new revision that was created by running the kubectl rollout history command, and that tells me that there's a new revision, which is revision 2, and the command that I ran to create the new revision was kubectl apply, which is a command that I ran to upgrade the images of my nginx containers. So that is good. Now I'm going to make the same change using another command, which is the set image command, and this is an alternate way of upgrading your nginx containers or your application. And so you run the set image command and you specify the new version of your application by using a name and value format. So the name is the nginx container, and the new version that I'm going to upgrade to is 1.12-Perl. So that's just another version of the nginx container. Okay, as soon as I run the command, I'm now going to run the rollout status to see the status of my upgrade. Okay, so the rollout is now successful. I'm now going to see the history by running the kubectl rollout history command, and I can now see that there's a new revision, which is revision 3, and the revision was created by running the kubecontrol set image command. So I now have 3 versions of my application. The first one was simply nginx. The second one was created when I ran the nginx 1.12 image, and the third revision was created when I changed my application to nginx 1.12-perl. When I run the kubecontrol describe deployments command, I can now see the image of my application containers updated to nginx 1.12-perl. Okay, so let's pretend that there was an issue with the last change. Let's pretend that our application doesn't really work well when I use the 1.12-perl image and users are reporting issues. So you're asked to roll back the last change that you made. So you can actually do that by running the kubecontrol rollout undo command and specifying the name of your deployment. And when you do that, of course, you can actually see the rollout status again, because that also kicks off a rollout. The rollout is now successful, and when I now run the history command to see the status of my revisions, you can now see that there is a new revision, which is revision 4, but you cannot actually see number 2. Now this is because when we did a rollback of our upgrade, it rolled back to revision number 2 because we were at revision number 3, and it actually created a new revision, which is revision number 4, and applied the same command that we used to create revision number 2, and also used the same definition file that we used at that time. So Kubernetes keeps a record of this internally, and so it takes us back to the version of container that we used in revision number 2. If I now run the kubecontrol describe command, I can now see that the image is now back to 1.12, which was actually revision 2. Okay, now let's take a look at another scenario where we have an error. So we will simulate an error by providing the name of an nginx image that doesn't really exist. So we'll make up a name, we'll call it 1.5-err. We know that this image does not exist, but our intention is to to simulate an error in deployment. So we've now updated our deployment definition file, and we're going to apply that changes using the kubecontrol apply command and specifying the deployment definition file as input. We'll also add the record parameter. Now when I run the kubecontrol rollout status command to monitor the status of rollout, you'll see that it's actually stuck at that point where it says 3 out of 6 new replicas have been updated. So we know that at this point in the backend, it's actually trying to bring down the old replicas and bring up new replicas, but it's actually stuck at 3 out of 6. Now let's try and see what's happening. If you run the kubecontrol get deployment command, you can see that our deployment is in a different state as to normal. The desired number of replicas is 6. However, the current number of replicas is 8, and up to date is only 3. Now if desired is 6, we would expect the current to be 6 and up to date to also be 6 and available to also be 6. But the recent change that we made is to update to an image that is not actually available. So if you run the kubecontrol get pods command to see the status of pods, you will notice that 5 of the old versions, which is the actual working versions, is available, and the new version, which is not actually available, there are only 3 pods created for that. So what's happened here is, as always, this is considered to be an upgrade, and the deployment object tried to terminate one instance from the old working version, so thereby bringing the total number of running pods to 5. and it tried to create 3 pods of the new version. However, the new version, as you know, is not right, and that's why you can see that the status is image pull back off. That basically means that the deployment is unable to pull the image from Docker Hub, and since it's unable to deploy any of the 3 images, any of the 3 pods, Kubernetes proactively stopped proceeding with the upgrade, and it proactively stopped terminating the old replica set, because it knew that if it did terminate all of the old replica set and tried to deploy all new replicas, then the users would be impacted because the new image does not exist. So it proactively stopped the upgrade, and it's now waiting for the new image to be available. If I now look at the rollout history command, I can now see that there's a new revision created, which is revision 5, and that was created by running the following command. I now know that there's an error with the image that I'm trying to download, so I'm going to undo that recent change by running the kubectl rollout undo command. And when I now look at the revision history, I can see that a new revision is created, which is revision 6, and it is going to revert to my 4th revision, which is actually now pulled out from the list of revisions. If you look at the image now, it is back to 1.12, and if I look at the pods, I can now see that I have 6 pods that are all in running state. Well, that's it for this demo, and I will see you in the next lecture.
Hello and welcome to this lecture. My name is Mumshad Manambet and we are learning Kubernetes for beginners. In this lecture, we will discuss about networking in Kubernetes. Let us look at the very basics of networking in Kubernetes. We will start with a single node Kubernetes cluster. The node has an IP address, say it is 192.168.1.2 in this case. This is the IP address we use to access the Kubernetes node, SSH into it, etc. On a side note, remember if you're using a Minikube setup, then I'm talking about the IP address of the Minikube virtual machine inside your hypervisor. Your laptop may be having a different IP, like 192.168.1.10, so it's important to understand how your VMs are set up. So on the single node Kubernetes cluster, we have created a single pod. As you know, a pod hosts a container. Unlike in the Docker world, where an IP address is always assigned to a Docker container, in the Kubernetes world, the IP address is assigned to a pod. Each pod in the Kubernetes gets its own internal IP address. In this case, it's in the range 10.244 series, and the IP assigned to the pod is 10.244.0.2. So how is it getting this IP address? When Kubernetes is initially configured, we create an internal private network with the address 10.244.0.0, and all the pods are attached to it. When you deploy multiple pods, they all get a separate IP assigned from this network. The pods can communicate to each other through this IP, but accessing the other pods using this internal IP address may not be a good idea, as it's subject to change when pods are recreated. We will see better ways to establish communication between pods in a while. For now, it's important to understand how the internal networking works in Kubernetes. So it's all easy and simple to understand when it comes to networking on a single node, but how does it work when you have multiple nodes in your cluster? In this case, we have 2 nodes running Kubernetes and they have IP addresses 192.168.1.2 and 1.3 assigned to them. Note that they are not part of the cluster yet. Each of them has a single pod deployed, as discussed in the previous slide. These pods are attached to an internal network and they have their own IP addresses assigned. However, if you look at the internal network addresses, you can see that they are the same.
the two networks have an address 10.244.0.0 and the pods deployed have the same address too. This is not going to work well when the nodes are part of the same cluster. The pods have the same IP addresses assigned to them, and that will lead to IP conflicts in the network. Now that's one problem. When a Kubernetes cluster is set up, Kubernetes does not automatically set up any kind of networking to handle these issues. As a matter of fact, Kubernetes expects us to set up networking to meet certain fundamental requirements. Some of these are that all the containers or pods in a Kubernetes cluster must be able to communicate with one another without having to configure NAT. All nodes must be able to communicate with containers, and all containers must be able to communicate with the nodes in the cluster. Kubernetes expects us to set up a networking solution that meets these criteria. Fortunately, we don't have to set it up all on our own, as there are multiple pre-built solutions available. Some of them are the Cisco ACI networks, Cilium, Big Cloud Fabric, Flannel, VMware NSXT, and Calico. Depending on the platform you're deploying your Kubernetes cluster on, you may use one of these solutions. For example, if you were setting up a Kubernetes cluster from scratch on your own systems, you may use any of the solutions like Calico or Flannel, etc. If you were deploying on a VMware environment, NSXT may be a good option. If you look at the Play with K8's labs, they use WeaveNet as their networking solution. In our demos in the course, we will be using Flannel. Depending on your environment and after evaluating the pros and cons of each of these, you may choose the right networking solution. If you go back and look at the demo where we set up a Kubernetes cluster initially using the kubeadmin tool, we set up networking based on Flannel. It only took us a few set of commands to get it set up, so it's pretty easy. So back to our cluster with the custom networking, either Flannel or Calico setup, it now manages the networks and IPs in my nodes and assigns a different network address for each network in the node. This creates a virtual network of all pods and nodes where they are all assigned a unique IP address. And by using simple routing techniques, the cluster networking enables communication between the different pods or nodes to meet the networking requirements of Kubernetes. Thus, all the pods now can communicate to each other using the assigned IP address. That's it for this lecture. We will now head over to a demo, and I will see you in the next lecture. Hello and welcome to this demo. In this demo, we will be looking at networking in Kubernetes. So I'm on my Kubernetes master node. So I have a set of pods that were deployed as part of a deployment. So I have 6 pods in a running state. And if I now run the kubectl get pods command with a -o wide option, I can see 2 additional fields, the IP and node. The node column tells me on which node the pods are running, and the IP is the internal IP that is assigned to each pod in the cluster. So as we discussed in the lecture, each node has an internal private network. In this case, for node 1 it's 10.244.1.0 and node 2 is 10.244.2.0, and the pods get an IP address within that range. And the communication between these internal networks is governed by the custom networking solution that we set up like Calico or Flannel. If you look at the IPs, you can see that the pods on node 1 have an IP under network 10.244.1, and so you have 1.94, 1.96 and 1.95, and under node 2 you have 10.244.2 series, and then you have 163, 164, and 176. Now these are all dynamic IP addresses, so they're not static, and the pods are not guaranteed to get the same IP every time. Well, that's it for now. We will look more into networking and ports when we discuss about services and when we go through the demo on services. Thank you for your time, and I will see you in the next lecture.
Hello and welcome to this lecture. My name is Mumshad Manambet and we are learning Kubernetes for beginners. In this lecture, we will discuss about Kubernetes services. Kubernetes services enable communication between various components within and outside of the application. Kubernetes services helps us connect applications together with other applications or users. For example, our application has groups of pods running various sections, such as a group for serving front-end loads to users, another group for running back-end processes, and a third group connecting to an external data source. It is services that enable connectivity between these groups of pods. Services enable the front-end application to be made available to end users. It helps communication between back-end and front-end pods and helps in establishing connectivity to an external data source. Thus, services enable loose coupling between microservices in our application. Let's take a look at one use case of services. So far, we talked about how pods communicate with each other through internal networking. Let's look at some other aspects of networking in this lecture. Let's start with external communication. So we deployed our pod having a web application running on it. How do we, as an external user, access the web page? First of all, let's look at the existing setup. The Kubernetes node has an IP address, and that is 192.168.1.2. My laptop is on the same network as well, so it has an IP address 192.168.1.10. The internal pod network is in the range 10.244.0.0, and the pod has an IP 10.244.0.2. Clearly, I cannot ping or access the pod at address 10.244.0.2 as it's in a separate network. So what are the options to see the web page? First, if we were to SSH into the Kubernetes node at 192.168.1.2, from the node we would be able to access the pod's web page by doing a curl, or if the node has a GUI, we would fire up a browser and see the web page in a browser following the address http 10.244.0.2. But this is from inside the Kubernetes node, and that's not what I really want. I want to be able to access the web server from my own laptop without having to SSH into the node and simply by accessing the IP of the Kubernetes node. So we need something in the middle to help us map requests to the node from our laptop through the node to the pod running the web container. This is where the Kubernetes service comes into play. The Kubernetes service is an object just like pods, replica sets, or deployments that we worked with before. One of its use cases is to listen to a port on the node and forward requests on that port to a port on the pod running the web application. This type of service is known as a node port service because the service listens to a port on the node and forward requests to the pods. There are other kinds of services available which we will now discuss. The first one is what we discussed already, node port, where the service makes an internal pod accessible on a port on the node. The second is cluster IP, and in this case the service creates a virtual IP inside the cluster
to enable communication between different services, such as a set of front-end servers to a set of back-end servers. The third type is a load balancer, where it provisions a load balancer for our application in supported cloud providers. A good example of that would be to distribute load across the different web servers in your front-end tier. We will now look at each of these in a bit more detail along with some demos. In this lecture, we will discuss about the Node Port Kubernetes service. Getting back to Node Port, few slides back we discussed about external access to the application. We said that a service can help us by mapping a port on the node to a port on the pod. Let's take a closer look at the service. If you look at it, there are 3 ports involved. The port on the pod where the actual web server is running is 80, and it is referred to as the target port because that is where the service forwards the request to. The second port is the port on the service itself. It is simply referred to as the port. Remember, these terms are from the viewpoint of the service. The service is in fact like a virtual server inside the node. Inside the cluster, it has its own IP address, and that IP address is called the cluster IP of the service. And finally, we have the port on the node itself, which we use to access the web server externally, and that is known as the node port. As you can see, it is set to 30,008. That is because node ports can only be in a valid range, which by default is from 30,000 to 32,767. Let's now look at how to create the service. Just like how we created a deployment, replica set, or pod in the past, we will use a definition file to create a service. The high-level structure of the file remains the same. As before, we have the API version, kind, metadata, and spec sections. The API version is going to be v1. The kind is of course service. The metadata will have a name, and that will be the name of the service. It can have labels, but we don't need that for now. Next, we have spec. And as always, this is the most crucial part of the file, and this is where we will be defining the actual services, and this is the part of a definition file that differs between different objects. Next, we have spec, and as always, this is the most crucial part of the file, as this is where we will be defining the actual services, and this is the part of a definition file that differs between different objects. In the spec section of a service, we have type and ports. The type refers to the type of service we are creating. As discussed before, it could be cluster IP, node port, or load balancer. In this case, since we are creating a node port, we will set it as node port. The next part of a spec is ports. This is where we input information regarding what we discussed on the left side of the screen. The first type of port is the target port, which we will set to 80. The next one is simply port, which is the port on the service object, and we will set that to 80 as well. The third is node port, which we will set to 30,008 or any number in the valid range. Remember that out of these, the only mandatory field is port. If you don't provide a target port, it is assumed to be the same as port, and if you don't provide a node port, a free port in the valid range between 30,000 and 32,767 is automatically allocated. Also note that ports is an array, so note the dash under the port section that indicate the first element in the array. You can have multiple such port mappings within a single service. So we have all the information in, but something is really missing. There is nothing here in the definition file that connects the service to the pod. We have simply specified the target port, But we didn't mention the target port on which pod. There could be hundreds of other pods with web services running on port 80. So how do we do that? As we did with the replica sets previously, and a technique that you will see very often in Kubernetes, we will use labels and selectors to link these together. We know that the pod was created with a label. We need to bring that label into the service definition file. So we have a new property in the specs section, and that is called selector, just like in a replica set and deployment definition files. Under the selector, provide a list of labels to identify the pod. For this, refer to the pod definition file used to create the pod. Pull the labels from the pod definition file and place it under the selector section. This links the service to the pod. Once done, create the service using the kubectl create command and input the service definition file, and there you have the service created. To see the created service, run the kubectl get services command that lists the service, the cluster IP and the map ports. The type is node port as we created, and the port on the node is set to 30008 because that's the port that we specified in the definition file. We can now use this port to access the web service using curl or a web browser. So curl to 192.168.1.2, which is the IP of the node, and then I use the port 30008 to access the web server. So far we talked about a service mapped to a single pod, but that's not the case all the time. What do you do when you have multiple pods? In a production environment, you have multiple instances of your web application running for high availability and load balancing purposes. In this case, we have multiple similar pods running our web application. They all have the same labels with a key app and set to a value of my app. The same label is used as a selector during the creation of the service. So when the service is created, it looks for a matching pod with the label and finds 3 of them. The service then automatically selects all the 3 pods as endpoints to forward the external request coming from the user. You don't have to do any additional configuration to make this happen. And if you're wondering what algorithm it uses to balance the load across the 3 different pods, it uses a random algorithm. Thus, the service acts as a built-in load balancer to distribute load across different pods. And finally, let's look at what happens when the pods are distributed across multiple nodes. In this case, we have the web application on pods on separate nodes in the cluster. When we create a service, without us having to do any additional configuration, Kubernetes automatically creates a service that spans across all the nodes in the cluster and maps the target port to the same node port on all the nodes in the cluster. This way, you can access your application using the IP of any node in the cluster and using the same port number, which in this case is 30008. As you can see, using the IP of any of these nodes, and I'm trying to curl to the same port, and the same port is made available on all the nodes part of the cluster. To summarize, in any case, whether it be a single pod on a single node, multiple pods on a single node, or multiple pods on multiple nodes, the service is created exactly the same without you having to do any additional steps during the service creation. When pods are removed or added, the service is automatically updated, making it highly flexible and adaptive. Once created, you won't typically have to make any additional configuration changes. That's it for this lecture. Head over to the demo and I will see you in the next lecture. Hello and welcome to this demo. In this demo, we're going to look at services in Kubernetes. So here I'm logged into my Kubernetes master node, and I'm just going to see the current status of deployments. So if I run the kubectl get all command, I can see there is a deployment created, and I have a replica set created, and the replica set in turn has around 6 pods created. I have a running application on my Kubernetes cluster. I'm now going to create a service to access this application or web service as an external user. For that, I'm going to go into my IDE and I will create a new folder called service, and inside that I'm going to create a new file named service definition.yaml. Okay, so under this file, as always, I'm going to start by creating the file structure. So I have API version, kind. So the API version is going to be v1, and under kind, from the drop down menu I can select service. I then give a name to my service, and that is going to be my app-service, and I'm not going to give any labels for now. Under spec section I have a type, and I'm going to set the type to node port because I'd like to expose my service on a node port. And then under ports I'm going to create the first element, and my target port is going to be 80 because that is a port that the nginx containers listen on. The port on my service is going to be 80 as well, and I'd like to expose the service on port 30008 on my node. Now the selector, we will add a selector to link my service to the pods. So for that I'm going to open up my pod definition file. I will open up the pod definition file on the right. I can now copy over the labels from my pod definition file into the selector. So that links my service to the pods. I'm going to now copy the contents of my service, and after making sure that the structure of my YAML file is good, I will create the service definition file on my Kubernetes master node. Okay, so now I have the service definition file, and now I will create the service using the kubectl create command. Okay, now if I run the kubectl get service command, I can see that my new service has been created, and it has a cluster IP, which is an IP assigned by Kubernetes for my service itself. And the type of the service is node port, and the port that it's mapped to is 30008. So now if I open up a browser and go to the port on my node on any of my worker node, which happens to be 56.3, and then I use the port 30008, I can actually see my nginx web server running on it. Okay, perfect. So that's it for this demo. We're going to see more about services and how the services, deployments, and replica sets all connect together when we look at an actual application, a demo application, in one of the upcoming lectures. That's it for now, and I will see you in the next demo.
Hello and welcome to this lecture. In this lecture we will discuss about the Kubernetes service cluster IP. A full stack web application typically has different kinds of pods hosting different parts of an application. You may have a number of pods running a front-end web server, another set of pods running a back-end server, a set of pods running a key value store like Redis, and another set of pods may be running a persistent database like MySQL. The web front-end server needs to communicate to the back-end servers, and the back-end servers need to communicate to the database as well as the Redis services, etc. So what is the right way to establish connectivity between these services or tiers of my application? The pods all have an IP address assigned to them, as we can see on the screen. But these IPs, as we know, are not static.
these pods can go down anytime and new pods are created all the time. And so you cannot rely on these IP addresses for internal communication between the application. Also, what if the first front-end pod at 10.244.0.3 need to connect to a backend service? Which of the three would it go to and who makes that decision? A Kubernetes service can help us group the pods together and provide a single interface to access the pods in a group. For example, a service created for the backend pods will help group all the backend pods together and provide a single interface for other pods to access this service. The requests are forwarded to one of the pods under the service randomly. Similarly, create additional services for Redis and allow the backend pods to access the Redis systems through the service. This enables us to easily and effectively deploy a microservices-based application on Kubernetes cluster. Each layer can now scale or move as required without impacting communication between the various services. Each service gets an IP and name assigned to it inside the cluster, and that is the name that should be used by other pods to access the service. This type of service is known as cluster IP. To create such a service, as always, use a definition file. In the service definition file, first use the default template, which has API version, kind, metadata, and spec. The API version is v1, kind is service, and we will give a name to our service. We will call it backend. Under specification, we have type and ports. The type is cluster IP. In fact, cluster IP is the default type, so even if you didn't specify it, it will automatically assume the type to be cluster IP. Under ports, we have a target port and port. The target port is the port where the backend is exposed, which in this case is 80, and the port is where the service is exposed, which is 80 as well. To link the service to a set of pods, we use selector. We will refer to the pod definition file and copy the labels from it and move it under selector. And that should be it. We can now create the service using the kubectl create command and then check its status using the kubectl get services command. The service can be accessed by other pods using the cluster IP or the service name. That's it for this lecture. Head over to the demo and I will see you in the next lecture. Hello and welcome to this lecture. My name is Mumshad Manambeth and we are learning Kubernetes for beginners. In this lecture, we will try and understand microservices architecture using a simple web application. We will then try and deploy this web application on multiple different Kubernetes platforms such as Google Cloud Platform as well as the Play with K8's platform. So let's get started.
I'm going to use the same sample application that everyone uses to demonstrate Docker. It's a simple yet comprehensive application developed by Docker to demonstrate the various features available in running an application stack on Docker. So let's first get familiarized with the application, because we will be working with the same application in different sections through the rest of this course. This is a sample voting application which provides an interface for a user to vote and another interface to show the results. The application consists of various components such as the voting app, which is a web application developed in Python to provide the user with an interface to choose between two options, a cat and a dog. When you make a selection, the vote is stored in Redis. For those of you who are new to Redis, Redis in this case serves as a database in memory. This vote is then processed by the worker, which is an application written in .NET. The worker application takes the new vote and updates the persistent database, which is
a PostgreSQL in our case. The PostgreSQL simply has a table with the number of votes for each category, cats and dogs. In this case, it increments the number of votes for cats as our vote was for cats. Finally, the result of the vote is displayed in a web interface, which is another web application developed in Node.js. This resulting application reads the count of votes from the PostgreSQL database and displays it to the user. So that is the architecture and data flow of this simple voting application stack. As you can see, this sample application is built with a combination of different services, different development tools, and multiple different development platforms such as Python, Node.js, .NET, etc. This sample application will be used to showcase how easy it is to set up an entire application stack consisting of diverse components in Docker. Let us see how we can put together this application stack on a single Docker engine using Docker run commands. Let us assume that all images of applications are already built and are available on Docker repository. Let us start with the data layer. First, we run the Docker run command to start an instance of Redis by running the Docker run Redis command. We will add the -d parameter to run this container in the background, and we will also name the container Redis. Now, naming the containers is important. Why is that important? Hold that thought, we will come to that in a bit. Next, we will deploy the PostgreSQL database by running the Docker run Postgres command. This time too, we will add the -d option to run this in the background and name this container DB for database. Next, we will start with the application services. We will deploy a front-end app for voting interface by running an instance of voting app image. Run the Docker run command and name the instance vote. Since this is a web server, it has a web UI instance running on port 80. We will publish that port to 5000 on the host system so we can access it from a browser. Next, we will deploy the results web application that shows the results to the user. For this, we deploy a container using the results-app image and publish port 80 to port 5001 on the host. This way, we can access the web UI of the resulting app on a browser. Finally, we deploy the worker by running an instance of the worker image. Okay, now this is all good, and we can see that all the instances are running on the host. But there is some problem. It just does not seem to work. The problem is that we have successfully run all the different containers, but we haven't actually linked them together. As in, we haven't told the voting web application to use this particular Redis instance. There could be multiple Redis instances running. We haven't told the worker and the resulting app to use this particular PostgreSQL database that we ran. So how do we do that? That is where we use links. Link is a command line option which can be used to link two containers together. For example, the voting app web service is dependent on the Redis service. When the web server starts, as you can see in this piece of code on the web server, it looks for a Redis service running on host Redis. But the voting app container cannot resolve a host by the name Redis. To make the voting app aware of the Redis service, we add a link option while running the voting app container to link it to the Redis container. Adding a -- link option to the Docker run command and specifying the name of the Redis container, which in this case is Redis, followed by a colon and the name of the host that the voting app is looking for, which is also Redis in this case. Remember that this is why we named the container when we ran it the first time, so we could use its name while creating a link. What this is in fact doing is it creates an entry into the etc host file on the voting app container, adding an entry with the host name Redis with the internal IP of the Redis container. Similarly, we add a link for the result app to communicate with the database by adding a link option to refer the database by the name DB. As you can see in this source code of the application, it makes an attempt to connect to a Postgres database on host DB. Finally, the worker application requires access to both the Redis as well as the Postgres database. So we add two links to the worker application, one link to link the Redis and the other link to link Postgres database. Note that using links this way is deprecated and the support may be removed in future in Docker. This is because, as we will see in some time, advanced and newer concepts in Docker Swarm and networking supports better ways of achieving what we just did here with links. But I wanted to mention it anyway so you learn the concept from the very basics.
Hello and welcome to this demo. In this demo, we're going to look at deploying our application on Google Container Engine or Kubernetes Engine on Google Cloud Platform. We will first start with setting up our Google Container Engine platform, and then we will proceed with creating the service definition files for pods and services, and then we will proceed with creating the pods themselves on Kubernetes and creating the services, and we will try and access our application that's hosted on the Kubernetes cluster. So let's get started. Okay, so here I have my Google Cloud console. I'm logged into my Google Cloud Platform with a test account, and this is my dashboard. We will now look at what Kubernetes Engine is. So if you look at the documentation page for Kubernetes Engine, you can see that it's a managed environment for deploying containerized applications on Google Cloud Platform. You can see its various features on this page. And so this is basically a pre-configured Kubernetes cluster that you can get on Google Cloud Platform with a single click. If you scroll down to the bottom, you will see a link to a quick start, and if you go in here, you will see basic information on how to get started with Kubernetes on Google Cloud Platform. So we're going to follow these instructions. So I'm logged into my Google Cloud Platform console, and when I go into the menu on the left, I have Kubernetes Engine on the left, so I'm going to click on that. And this takes me to the Kubernetes dashboard. So I do not have any cluster for now, so I'm going to click on Create a Cluster. And this brings up the form to create a cluster. So I'm going to give a name, example voting app. Just going to add a description. It is a Kubernetes cluster to deploy our example voting application. I will leave everything else as is at the default, and I'm going to click on Create. So what this does is it basically creates a Kubernetes master node and 3 worker nodes, and that's going to take a few minutes to deploy. And once it's ready, I will see a green check mark. Now I just clicked on the Google Cloud Shell in the top right corner. What this is this gives me a temporary shell that I can work with. So it is in this shell that I'll be running all my Kubernetes commands. Now it takes a few minutes for the cluster to be set up. So what I'm going to do for now is I'm going to click on the connect button on the example voting app cluster, and it gives me instructions on how to connect to my Kubernetes cluster. So in my Google Cloud Shell, I could run this command which is gcloud container clusters get credentials. I could run the command to get the credentials to connect to my Kubernetes cluster, and then once that command runs successfully, I will then be able to use the kubectl command line to interact with my Kubernetes cluster. So I'm going to copy the command and I will run it. I'm not sure if it's going to work because the cluster has not fully been set up yet.
And yes, as you can see, it gives me a warning that states the cluster is still not running, so I'm going to wait for the cluster to start up. And yes, as you can see, I now have a green check mark next to the example voting app, and that indicates that the cluster is fully set up. So I'm going to rerun the command again, and as you can see, it says the kubeconfig is configured correctly. I should now be able to run kubectl commands on my Kubernetes cluster from this terminal. I'm going to run the kubectl get nodes command to get a list of nodes available in my cluster. As you can see, there are 3 nodes available and they're all in ready state. And I could run the kubectl get pods command to see a list of pods. And since I haven't created any pods, I do not see any. And I could run the kubectl get services command to get a list of services. But as you can see, there's one service already created, and that's a default service created by Kubernetes. So we can leave that at that. So I now have my Kubernetes cluster ready on Google Cloud Platform. I'm now going to create all the definition files for pods and services so that I can then use those files to create the pods and services I need on the Kubernetes cluster. So I have opened an IDE on my laptop, and I've created a folder called example voting app kube, and in this folder I'm going to create the different files needed. So first I'm going to start with a pod definition file for my voting app. So I'm going to call it voting app pod.yaml. Okay, now in this file I'm going to define my YAML definition. I'm going to start with version as we discussed in the lecture. So I have API version, kind, metadata, and spec. So always remember, these are the 4 major sections, so I will always start by just putting all the 4 there, and then I will go ahead and start filling in values for each of these sections. So I have all the 4 defined. Now I'm going to specify the version, and that's going to be v1. I then have the kind, which is pod, because I'm now creating pods. And under metadata, I'll always start with name, so the name is going to be voting app pod, so that's the name of my pod. And then I always have labels. As you can imagine, labels are used to tag the pods or resources that we create on Kubernetes. This way you can later search these resources based on these labels. So the labels are later used with services to allow services to search and find out the respective pods. So I'm going to create a label named name. I'm going to give that a value of voting app pod. And then I'm going to add a label called app, and I'm going to call it demo voting app. So my application is demo voting app, and the name of this pod is voting app pod. I'll use the same format of labels for all my pods and services. Okay, so the next is a spec. So spec for specification. Since this is a pod, I'm going to have containers inside it. So everything that comes under spec section is dependent on the type of definition you're creating. Since this is a pod, I will have containers. If I were creating a service, then I might have ports under it. So I'll start with containers, and under containers we provide an array of containers. So I create an array with name as voting app and the image that is used to deploy the container. What I'm going to do now is I'm going to go to Docker Hub and search for Docker samples, and that's where I can find all the images for my voting application. And there you can find the example voting app. What I need is the vote app itself. So I'm going to copy the name for the example voting app image, and that's the image that I want the pod to use. So I'm going to specify the name of the image under the image section. And then finally, I need a port to be exposed. So I'm going to add a port section, and under that I can provide a list of ports In this case, I'm just going to have one port, and I'm going to call that, and that's going to be 80. Okay, so now I have my voting app pod definition file ready. So if you look at it, first I have the API version, which is v1, and then I have the kind set to pod. I have some basic metadata where I'm providing the name of the pod and some labels. And then I have specification under which I have containers. So since this is a pod, I have containers under specification. And we only have one container per pod, which is why I only have one image specification under containers. So the name is voting app, the image is the name of the image that I want the pod to use, and then the image exposes port 80, so I'm going to add the port 80 under the port section. Okay, now I'm going to use the same file to create other pods. So I'm just going to copy the same file and create a duplicate of that, and under that I'm going to have worker, so worker app. I will now create a pod for worker. So for worker, everything remains the same. The API version is going to be v1, the kind is going to be pod. I'm going to change the name to worker. I'm also going to change the label to worker. And under specification, I'll change the name of the container to worker and the image as well. So we'll change the name to worker, and I'm going to change the name of the image. So I'll go back to the Docker Hub. I'll find the worker image, and then I'm going to copy the name of the image and place it there. Okay, so I have my worker container. Now the worker does not expose any ports because it's not a web application, so I'm just going to remove the port section for the worker. Okay, I'm going to create another copy of the voting app, and I will now create a pod for the result app. So I'm going to name it result-app-pod. Then again here everything remains the same except the name, so I'm going to change all the name to result. The name of the container also from voting to result, and then I'm going to go to Docker Hub and get the name of my result image. Okay, and I'm going to replace the name of the image with the result app image name, and the result app exposes port 80 because it's a web application, so I'm going to leave the port section as it is. Okay, so I'm done with all the three application pods. I have two pods remaining, which are for Redis and the Postgres database. So I'm going to create a new file for Redis pod. I could have just copied, but I'm just going to create a new file for the Redis pod. I will name it redis-pod.yaml, and I will copy the contents from the voting app again. And this again, it's all going to remain the same except for the names. So the name is going to be Redis. Instead of voting app, I'm going to rename that to Redis-pod. The label as well to Redis-pod. And the name of the container to Redis, and the image name is going to be Redis. The port is now going to be 6379 because that's the default port that Redis exposes. Okay, so I have my Redis pod. I'm going to create a copy of that, and I'm going to now create the Postgres database pod. And in the Postgres pod, I'm going to first rename all the names and labels to Postgres. And the name of the container will now be Postgres, and the name of the image is going to be Postgres with a tag of 9.4 because that's the version that the example voting app uses. And the container port is now going to be 5432 because that's the port that Postgres listens to by default. Okay, so I now have all my 5 pods. Now the next step is to create services so that these pods, once deployed, can communicate with each other. So first I'm going to create the internal services. So I'm going to create a new file. I will name the file redis-service.yaml, Okay, so again, in this file, I will define the base structure, which is going to be API version, kind, metadata, and spec. The API version is going to be v1. The kind in this case is going to be service. Metadata is going to have name, which is going to be Redis, and labels. Under labels, I'm going to have name, which is going to be Redis service, and the application is going to be demo voting app for all of the pods and services. The specification, so since this is a service, we're going to have ports under specification. Earlier, when we created a pod, we had containers under specification. Now we have ports. So what this says is under ports, I'm going to provide a list of ports. To start with, first it's going to be 6379, and I need to give a source port and target port. So the source port is going to be 6379 and target port is going to be 6379. So what is it going to listen on? Where does it listen from? So let's say we have 5 different pods running. When we run the pods, when we create the pods, we'll have 5 different containers running. We'll have the Postgres database, Redis, the voting applications, etc. Now, when we create this service, we're basically telling the service to listen on port 6379 and forward that to port 6379. But where exactly is it listening from, and what exactly does it forward to? So we need to link this service to one of the pods that we created so that it knows to work with that particular Docker container in that pod. So how do we specify or link this service to a particular pod that we have created? For that, we use selectors. Under the specification, we create a section called selector. So under the selector section, we provide a list of filters. So what do we filter on? We filter by list of labels, and this is why we labeled each of our pods with a different name. For example, if we go back to our Redis pod, we can see that under the labels it has a name and an app. So if I copy that whole section as is and paste it under the selector section, when the service is created, so it will link the service to a pod based on the filter that we have provided here. So in this case, it is going to link this service to the Redis pod because it is the Redis pod that has the label based on these filters. Okay, so we have the Redis service. Now we're going to create another service. So I'm going to copy the Redis service and create a Postgres service. And this is for the Postgres database. This is for exposing the Postgres database to the worker and the result app. So in this Postgres service file, we're going to rename the name of the service to DB because this is the name that our application listens on. So remember that the services should be named based on what the other application is looking for. We know that the worker app tries to connect to a service on the host named DB. So this service should be named DB or whatever our applications are looking for. The label is going to be DB service. The port in this case is going to be 5432 because that's the port that the Postgres database listens on. And the selector in this case is going to be the selectors, the labels we have defined for Postgres. So I'm going to go back to the postgres-pod.yaml file and I'm going to copy the labels under the Postgres pod. I will put that labels under the selector section. So this enables the the Postgres service. When it is created, it will link the Postgres service to the pod that it can retrieve based on these filters we have provided here. Okay, so the next step is to create a load balancer or external service so that our users can access our application. So what we're going to do is we're going to copy the Redis service and we're going to create a new service and we will call that the voting app service, because this service is going to expose the voting app to the external world through a load balancer. So we're going to modify the name to voting service. We will change the labels to voting service. The port is going to be 80 because that's the port that the container exposes. And we will need to change the selector to link the service to the voting app by copying the labels from the voting app and putting them under the selector section. Okay, now we have our voting service ready, but like the Redis and the Postgres services, this is not an internal service. So by default, the services are created with a type called cluster IP. The services created with cluster IP type are only available within the cluster. To enable the service to be accessible outside the cluster, we must change the type of the service to something else. So in this case, we're going to change the type of service to load balancer. Okay, so we are ready with our voting app service. Similarly, another service that we want to expose outside is the result app. So we'll create a copy of the voting app service and we'll create a result app. And in the result app, we're going to rename the service from voting to result. Similarly, we're going to relabel the service from voting to result. But remember, for these services, the labels doesn't really make sense. So you really don't need to have these labels for these services because we are not requiring these services from any other resource or selecting these services from any other resource. So it doesn't really matter, but it's a good practice to label the services appropriately. The type is going to be load balancer, the ports are going to be 8080, but the selector in this case is going to be the selector for the result app. So I'm going to copy the labels from the result app and I'm going to put it under the selector section for this service. Okay, so I now have the service ready for the result app. So I now have 5 pods and 4 services. Out of the 4 services, 2 of them are for Redis and Postgres database, so they are internal service, and I have 2 services for the external users, which are for the voting app and the result services. So I'm all set with my definition files, and now all I need to do is go to the Kubernetes cluster and deploy these services. Now, what I'm going to do is to, in order to copy these files over, I'm going to check in these files into my GitHub account. I have created a new repository on my GitHub account, and I've uploaded all these files into this account. So what I'm going to do is I'm now going to copy this, the link to this GitHub repository, and on my Kubernetes cluster, I'm first going to clone the repository so that I can get all the files on there. Okay, I'm now going to clone the repository using the git clone command. Okay, so that's completed. I should now have a new folder named Kubernetes Example Voting App. And that's there, so I'm going to go into the Kubernetes Example Voting App and I can see all the files that I just created. Great. So now I'm going to go ahead and create these pods and services one by one. I will start with the voting app. So what I want to do first is I just want to start simple. So I'm going to deploy the example voting app, the voting piece of it alone, and I will create the service and I will just try to access that voting app alone first, just to make sure that I'm able to deploy that and access that from a browser. So I will use the kubectl create command -f, and then what I'm going to start with is the voting app pod. Okay, so I'm going to give the name of the pod definition file, and that is going to be voting app pod. Okay, great. So I see the message that voting app pod is created, and I will just wait for it to run. So So if I do a kubectl get pods command, I can see that it's running. So if you look at the ready state, it's 1/1. That means that one containers is running, and that's good. Next, to be able to access this voting service from a browser, I need an external service to be created so that I can access it. So I'm now going to create the service for the voting app service. So that's going to be kubectl create-f voting app service.yaml. Okay, so I've got the message that says service is created. I could now list the services using the kubectl get services command. Okay, so if you look at the output of that, it says there's a voting service that is being created, and the status is pending. So it's currently deploying the load balancer. So if I go to the discovery and load balancing section in the UI, I can actually see that the voting service is in the process of creating a load balancer service. So I'll just have to wait and give it a few minutes for it to deploy the load balancer service. The load balancer service only works on public cloud platforms such as Google Cloud and AWS. So this is in fact relying on the Google Cloud load balancer. When I click on refresh, it's refreshed the status, and now it's okay. I can now see the external IP address. So if I simply take the external IP address and go to a browser, I should now be able to see my application. Or in the UI above, you have a link that will take you directly to our application. So when I click on that, I can now see the cats versus dogs interface, and my voting app, the first piece of the first component of our application, is up and running, and the load balancer has been configured successfully. So that's great. Next, I will proceed with the remaining components. So I will first create the Redis pod, because my voting app is dependent on the Redis pod. I will use the command kubectl create-f and redis pod.yaml. Okay, so the Redis pod is created. If I do a kubectl get pods command, I can see that it's already running, so that's good. And now I will create the Redis service so that my Redis pod is available to my other pods. So I will do a kubectl create-f redis-service.yaml, and that creates the Redis service. If I do a kubectl get services, I should now see a new service created. But if you look at the type, it says cluster IP, and that indicates that it's an internal service. Okay, so at this point I have the first few components deployed. I will now proceed with the Postgres database. So I will create the Postgres database pod. So I will run the kubectl create-f postgres-db-pod.yaml, and I get the message back saying the pod has been created. If I run a kubectl get pods command, I can see that it's in the process of creating the container. So that may take a few minutes depending on the size of the image, etc. But I really don't have to wait for creating the service, so I could go ahead and create the service for the Postgres database. So I'm going to do a kubectl create-f postgres-service, and this will create my Postgres service. This service will enable the other components to access my Postgres database. So if I run the kubectl get services command, I can now see that I have the DB and it's of type cluster IP. And next I will deploy the worker app. So I will run the kubectl create-f or worker pod. I will run the kubectl get pods command to see that the worker app pod creation is in progress. I don't have any services for that because no other components are actually relying on the worker pod. I'm now going to create the result app pod. So I will run the kubectl create command and provide the result app pod definition file. Okay, so the result app pod definition file has been created. I will also create the result app service for making the result app available externally. So I will run the kubectl create-f result app service.yaml command. So I have all of my pods running and I have all of my services up and running. The result service is still pending as it's busy creating the load balancer. So I'm going to go into the UI and refresh. And as you can see, the load balancer service configuration for result service is in progress. So I'm going to wait for it to be available. Okay, so it's ready. And when I click on the load balancer IP, I can see that it's up and running. And if I now go and cast my vote, I can see the result being updated instantly. So this confirms that our application is working and it's all integrated with each other using services. Okay, so that's the end of the demo. We have successfully created a cluster on a Kubernetes cluster on Google Cloud Platform. We have created the files required to create pods and services. And we have hosted our application on the Kubernetes cluster on Google Cloud Platform. That's a simple and very basic demo. Hope you enjoyed it. Thank you very much for your time, and I will see you in the next lecture.
Hello, and welcome to this demo. So this is what we saw in the last demo. We deployed pods and services to keep it really simple. But this setup has its own challenges. Deploying pods doesn't help us scale our application easily. Also, if a pod was to fail, it doesn't come back up or deploy a new pod automatically. We could deploy multiple pods one after the other, but there are easier ways to scale using replica sets and deployments as we discussed in the lectures. Let us now improvise our setup using deployments. We chose deployments over replica sets as deployments automatically create replica sets as required, and it can help us perform rolling updates and rollbacks, etc. Deployments are the way to go. So we add more pods for the front-end applications, voting app and result app by creating a deployment with 3 replicas. We also encapsulate database and workers in deployments. Let's take a look at that now. Okay, so here I have a new project that I've created in my PyCharm editor, and I call it example voting application -Kubernetes -v2. So I have copied over all the files that I created in the previous demo, and in this demo we're going to modify our setup to convert these pods into deployments. So as you can see, the files that I have are Postgres pod and the service for the Postgres service. Similarly, I have a pod for Redis and the service for Redis, a result app pod, result app service, voting app pod, voting app service, and a worker app pod. Now our goal is to convert all these pods into deployments. The services, we can leave them as is for now. Okay, so I'm going to look up the Kubernetes.io documentation page to pull up the template required to create a deployment. So I'm just going to go to the documentation page and search for deployment and click on deployments, and here I have the template that I need to create a new deployment. So I'm going to go back to my editor and I will now create a new file for deployment. I will name that redis-deployment.yaml. I will also open the Redis pod definition file that I created earlier in another tab. So on the right I have the Redis pod, and on the left I have the Redis deployment.yaml file that I'm going to populate now. I can copy everything from the template up until the template section, and then the template section would be the contents in the Redis pod definition file on the right. So I have the template. I'm now going to rename the deployment from nginx to Redis. I will set only one replica for the Redis, because I only need one instances of my databases. And then under selector, I will now copy the labels under my Redis pod definition. So I'm going to copy the labels and put them under the match labels section under selector. And then the template section would be everything in the Redis pod section, Redis pod definition file, except for the first two lines, which are API version and kind. I'm going to copy all of that. I will paste it under template, and as you can see, as everything from the second line onwards, that is from the name line 15 onwards to the bottom, are not aligned properly, so they should be falling under the metadata section. But since I copied it over from the other file, they're not aligned. So I'm just going to select all of that, everything that I pasted from the second line onwards, and then hit tab twice, so that they all move under the template section or the metadata section properly. Okay, so I have now aligned it. So I now have my deployment definition file. The name of the deployment is going to be Redis-deployment. The number of replicas is going to be 1. The selector matches the labels under the same labels under the template section, and the template section has everything that I created earlier for creating the pod. So I'm now done with my Redis deployment. I don't need the Redis pod definition file anymore, so I'm going to get rid of that. So I've deleted the Redis -pod .yaml file. Now I will repeat the same step for all the other components, which is the next one is DB, which is the Postgres database. So I'm going to open the Postgres -pod.yaml definition file on the right. I will create a new file called Postgres-deployment.yaml. Okay, I will now copy over the deployment definition template from the documentation page. I will rename the deployment to Postgres. The app, I'm going to leave the app to demo voting app. I just remembered that I didn't do that for the Redis deployment. So first I'm going to change it here, demo-voting-app, and I'll just also go to the Redis deployment and set the same there. In this setup we're really not using this label, but it's just good to have all of them tagged with the same label, as they're all part of the same application. Okay, now under the selector section, I'm going to copy over the labels on the Postgres pod, and then I'm going to copy everything from metadata and spec on the right and move it under template section. Okay, so I will paste once, then I'll select everything from line 15 and hit tab twice so they're aligned properly. Okay, so I have the Postgres deployment file definition file ready. I'm now going to get rid of the Postgres pod.yaml file. Okay, next up is the worker pod at the bottom. So I'm going to open up the worker app pod definition file on the right, and I will create a new worker app deployment.yaml file on the left. Again, I will copy a template for deployment. I will set the name to worker-app-deployment. and the app name label is going to be demo voting app. I also need just one replica for the worker. Now under match labels, I'm going to copy the labels from the pod definition file. I will then copy over all the contents of the pod definition under the template section of the deployment. I'm now going to get rid of the worker app pod definition file, as we no longer need that. Okay, now we are left with two pod definition files, which are for the voting app and the result app. We will start with the voting app. So I'm going to open the voting app pod definition file on the right, and on the left I'm going to create a new file for voting app deployment. I'm going to copy over the template for deployment definition and set the name to voting app deployment. One replica. We will start with one replica for now, and we will update it or scale it up to 3 replicas while it's running. I will copy over the labels and make sure they're aligned properly under match labels, and then copy all the section of metadata and spec and then align them properly in the voting app deployment file. Okay, we're now set with the voting app deployment.yaml file, and we can now get rid of the voting app pod.yaml file. Alright, and we are only left with the result app. Again, I will open the result app-pod.yaml on the right, and I'm going to create a new file called result app-deployment. We'll now copy the template for deployment, rename it to result-app-deployment, set the app name label to demo voting app. I will leave the replicas to 1 for now, and we will increase the replicas later. I'm going to copy over the labels into the match labels section, and under template I'm going to copy over the metadata and spec section. Okay, I've made sure that they align properly, and I can now get rid of the resulting app pod.yaml file. Okay, so I'm done with all the changes I need to make. I now have deployments instead of pods, and I have all the services, which I'm okay to work with as it is. The services are directly linked to pods using selectors, so I don't have to make any changes on them. Okay, so I now need to get these files onto my Kubernetes master to deploy them, and so I'm going to first get them on my GitHub. I'm going to create a new repository on my GitHub account called example voting app Kubernetes-v2. Okay, I will make that as a public repository, and then I'm going to copy the URL to the repository, and in my JetBrains IDE I'm going to go into VCS tab and enable version control. I'll select Git. This will create a Git repository locally on my folder. I can now right click, go to Git, commit directory, and add a commit message called initial commit. So I'm going to commit my repository. I'm going to commit that and push, and here I can define the remote repository URL, which is the URL to my GitHub repository that I just created. Okay, so I have now added a remote origin and pushed the files onto my GitHub repository. So if I now, I will now wait for the push to be successful. So the push is successful. If I now go back to my Git repository, I can now see that all my files are there. I'm going to copy the URL and then go to my Kubernetes master and clone my repository there. Okay, once it's cloned, I'm going to go into the folder and I can see all the files that I just created. Great. So all I need to do now is run the kubectl create command -f and with a dot, and it will simply go ahead, pick each file and create these necessary deployments and services as defined in those files. If I run a kubectl get all command, we can now see that they're in the process of creation. The deployments and services are being created. I'm going to give it some time for it to completely create and deploy the necessary pods. Okay, I can now see that all my deployments, all my pods are in running state. I only have one replicas for all of my deployments, so they're good. And if you look into the services section, you can see that my services are exposed on node port, on port 31061 and 30035. The voting service is on 30035 and the resulting service is on 31061. And I can use any IP address. I can use the IP address of any of my nodes, and along with these ports, I will be able to access the front-end applications. So I'm going to use the IP of one of my nodes, which is 192.168.56.72, and the port 30035, and that takes me to the voting application. I can now cast my vote, and if my voting app is successfully able to reach the Redis service, you will be able to see a check mark indicating that your vote has been accepted. If you look at, if you would like to see the result, again, use the same IP followed by 31061, which is where the result app is exposed. So as and when I change the vote now, I can see the result changing as well. Okay, now if you look at this page, you can see that the vote is processed by container ID voting app deployment, followed by the ID of the container. Now it's the same right now, even after you refresh the page, because we only have one replica, so it's always going to one pod. What we would like to do now is scale our application. So imagine that the number of users casting their vote or viewing the result have increased. So we would like to modify the number of replicas and scale the application to 3, as you can see in this diagram. All we need to do is modify the deployment definition file. So I'm going to use the VI editor and modify the voting app deployment.yaml file and change the number of replicas to 3. I'm now going to save that, and I'm going to run the command kubectl apply -f followed by the deployment definition file, and as you can see, the deployment has been configured. If I look at the deployments right now, I can see that the desired number of deployments is 3, but we only have 1 available now, so we'll give it some time to spin up the other 2 pods for the voting app. I now have 2, and I now have 3. So I now have 3 pods running for casting the vote. I don't have to make any other changes. The service that we have created for the front-end application automatically picks up the additional pods, and it automatically balances load between them, so we don't have to worry. As you can see, the pod that is serving the application right now is TLS8C. So we're going to try and refresh the page and see if it takes us to the other pods. It's still TLS8C, and now you can see it takes us to the other pod, which is FKJ8F. It's just going between 2 pods right now, but if you keep going at it, you'll see that it ultimately takes you to the 3rd pod as well. So now you can see it keeps going between all the 3 pods, and all you need to do is cast your vote, and your result will be reflected. And each time you cast a vote, it is handled by a new or a different pod, and all of that just works fine. So it's that easy to scale your application once your deployment is configured. Okay, I'm now going to repeat the same for the result app. I'm going to edit the result app deployment file and update the number of replicas to 3. I will now update the change using the kubectl apply command and provide the result app deployment file. When I now run the kubectl get deployments command, you can see that the result app deployment, the desired count is 3. There's only 1 available right now, and on refreshing you can see that there are 3 available. So now if I go to go and refresh my result app, it's actually coming back on a new it's being served from a new pod, but we do not really have the container ID being displayed on this page because it's just not developed that way. So but you can see the available number of result pods have been scaled up as well. Let us now focus on the front-end applications, the voting app and the result app. We know that these pods are hosted on different nodes. In this case, let's just assume that they're hosted on 4 different nodes. The services with the type currently set to node port help in receiving the traffic on the ports on these nodes and routing and load balancing them to the appropriate pods. But what IP address would you give your end users to access the applications? You could access any of these 2 applications using IP of any of the nodes and the high-end port the service is exposed on. That would be 4 IP and port combination for the voting app and 4 IP and port combination for the result app. But that's not what the end users want. They need a single URL like example-vote.com or example-result.com so that they can access the application by just going to those URLs. Now, one way to achieve this in my current VirtualBox setup is to create a new VM for load balancer purpose and install and configure a suitable load balancer on it like HAProxy or Nginx, etc. The load balancer would then reroute traffic to underlying nodes and then through to the underlying pods to serve the users. Now, setting all of that external load balancing can be a tedious task. However, if I was on a supported cloud platform like Google Cloud, for instance, I could leverage the native load balancer to do that configuration for me. Kubernetes has support for getting that done for us automatically. All you need to do is set the service type for the front-end services to load balancer. Remember, this only works with supported cloud platforms. If you set the type of service to load balancer in an unsupported environment like VirtualBox, then it would simply be considered as if you set it to node port, where the services are exported on a high-end port on the nodes. That would result in the same setup we had earlier. Let us take a look at how we can achieve this on Google Cloud Platform. So I'm now going to go back to my files that I've created in my IDE, and I'm going to update the number of voting app replicas from 1 to 3 so that I don't have to scale it up later. I would like the service to be deployed with 3 replicas to start with, and I will update the number of replicas on the worker app also from 1 to 3. This is just to demonstrate how easy it is to deploy multiple instances in the first deployment itself. I will now make a change to the service types. Earlier I had the service type set to node port, and as we discussed, I'm going to change that to a load balancer type. So I'm going to select the voting app-service.yaml file and change the type to load balancer, Similarly, I'm going to my result app, and I will also change my type of service to a load balancer. I'm now going to commit my changes to my Git repository. I will say update deployments and service type. Okay, so I now have my files committed and pushed to my Git repository. I can now go log into my Google console and try and deploy the same application over there. Okay, now I'm logged into my Google Cloud Console. I'm in the Kubernetes clusters section, and I have one cluster already created and ready for me to deploy my application on. Click on the connect button, and it opens up the connect to the cluster wizard. And here I could simply click on the run in Cloud Shell to open up the Cloud Shell and establish connectivity to my Kubernetes master. Okay, so I just need to hit enter to authorize and get into the Kubernetes master node. Okay, and what I will first do is I will simply download or clone my Git repository. So I'm going to say git clone, then copy the URL of my repository. Okay, so once I have my example voting app version 2 available, I will then create all the files, create all the components needed by simply running the kubectl create-f dot command. This will go in, pick up each file, and create the defined Kubernetes objects. I will wait for some time and give it some time for these objects to be created. I will run the kubectl get all command to see a list of all the objects that are being created. As you can see, it's already created a set of services, deployments, etc. We will first focus on the deployments. So as you can see, it's already created and successfully some of the deployments, and we'll just wait for it to finish all. Okay, so it's deployed a set of services, and I can now access my application using the services. Now when I run the kubectl get services command, in the output you can see there's something new this time, something that we didn't see before, which is the external IP. Now as you can see, the type of service on result service and voting service is set to load balancer, and that has invoked a call to the Google built-in or native load balancer functionality, and it's automatically created an external load balancer, and the IP that you see in the external IP column is the IP of the load balancer that can be used by us or by the external users to access our application. Okay, I'm going to first access the result app. All I need to do is copy the IP, put it in a browser, and you can see the result app. Similarly, I'm going to open up and access the voting service, and that's the voting app. Okay, I'm now going to cast a vote and make sure it's reflected in the result page. Okay, I've now casted a vote, and I can see the result getting updated. And every time you cast a vote, you can see that it's being handled by a different pod, one of the 3 pods that we deployed. Okay, so that's it for this demo. In this demo, we have improvised upon our setup using deployments to create the different components of our application, and we have used services with a type load balancer that internally invokes the native load balancing functionality of the underlying supported cloud platform, and makes it easy to integrate Kubernetes with the load balancers of the cloud platform. So thank you so much for your time, and I will see you in the next section. We are at the end of the Kubernetes for Beginners course. I hope I have covered enough topics to get you started with Kubernetes. We started with containers and Docker, and we looked what container orchestration is. We looked at various options available to set up Kubernetes. We went through some of the concepts such as pods, replica sets, deployments, and services in Kubernetes. We also looked at networking at a very basic level in Kubernetes. We also spent some time on working with kube control commands and Kubernetes definition files. I hope you got enough hands-on experience in developing Kubernetes definition files. And finally, we also saw how to deploy a sample microservices application on Kubernetes on Google Cloud Platform. I will be adding additional topics to the course in the near future, so watch out for an announcement from me in case you need me to cover any other topics. Feel free to send me a message or post a question, and I will try my best to add a new lecture on it. We also have an assignment as part of this course, so if you have time, please go ahead and develop your own solution and submit your assignment. Feel free to review other students' assignments and share your views on them. It was really nice having you for this course. I hope you gained enough knowledge and experience to get started with Kubernetes at your work or otherwise, and I wish you good luck in your Kubernetes journey. See you in the next course. Until then, goodbye.
Hello there. Before we begin, I want to spend a minute on the Kubernetes series of courses. Kubernetes is one of the most trending technology in cloud computing as of today. It is supported on any cloud platform and supports hosting enhanced and complex applications on various kinds of architectures that make it a vast and complex technology. There are a set of prerequisite knowledge required, such as containers, applications, YAML files, etc. A lot of topics to discuss, a lot of concepts to cover, such as the architecture, networking, load balancing, a variety of monitoring tools, auto-scaling, configuration, security, storage, etc. There are students from different backgrounds, such as the absolute beginners to Kubernetes, or those with some experience looking for specialized knowledge in administration, or those from an application development background. And there are 2 certifications in the mix as well. One for the administrators and another for the application developers. Covering all of these topics for all of these students in a single course is an impossible task. Which is why we created a 3-course series so each course can target specific audience, topics, and certifications. The Kubernetes for the Absolute Beginners course, the Certified Kubernetes Administrators course, and the Certified Kubernetes Application Developers course. Let's look at what we cover in each of these courses. The Kubernetes for the Absolute Beginners course helps a beginner having no prior experience with containers or container orchestration get started with the concepts of Kubernetes. As this is a beginner's course, we do not deep dive into technical details. Instead, we focus on a high-level overview of Kubernetes, setting up a simple lab environment to play with Kubernetes, learning the prerequisites required to understand and get started, understanding the various concepts to deploy an application, such as pods, replica sets, deployments, and services. This course is also suitable for a non-technical person trying to understand the basic concepts of Kubernetes, just enough to get involved in discussions around the technology. The Kubernetes for Administrators course focuses on advanced topics on Kubernetes and in-depth discussions into the various concepts around deploying a high availability cluster for production use case, understanding more about scheduling, monitoring, maintenance, security, storage, and troubleshooting. This course also helps you prepare for the Certified Kubernetes Administrator exam and get you verified as a Kubernetes administrator. The Kubernetes for Developers course is for application developers who are looking to learn how to design, build, and configure cloud-native applications. Now, you don't have to be an expert application developer for this course, and there's no real coding or application development involved in either this course or the certification itself. You only need to know the real basics of development on a platform like Python or Node.js. This course focuses on topics relevant for a developer such as config maps, secrets and service accounts, multi-container pods, readiness and liveness probes, logging and monitoring, jobs, services, and networking. This course also helps you prepare for the Certified Kubernetes Application Developer exam. All of these courses are filled with coding exercises and quizzes that will help you practice developing and deploying applications on Kubernetes. Now remember that there are some topics that overlap between these courses, so we recap and discuss them as and when required. Now you don't have to take these courses in order. If you're an administrator, you may choose to take the beginners as well as the second course and get yourself certified as a Kubernetes administrator, or take the beginners course and the developers course to get yourself certified as a Kubernetes application developer, which I'd say is the easier of the two if you were to ask me. So if you're ready, let's get started.